liking it? Very bright. Or maybe I'm still jet lagged. Yeah, maybe you can. Let's get started. Everything okay. That's worse. Okay, that's okay. Maybe you just needed to make it worse so that I feel better. That's what happens. Make your systems less reliable and then make them a little bit better. People reliable they were in the first place. That's a marketing tactic, not an engineering method. But maybe you came to learn about marketing here. Now, if you want to make money, you got to know all of that. Okay, anyway, let's get started. Today, we're going to continue the lecture on flash memory, and we're going to dive a little bit deeper into robustness issues. I must say that these lectures are one of a kind. You cannot find these anywhere else, and I'm proud of them for that reason. If you go to regular computer architecture course all across the world, they don't even know what flash memory is. I'm joking, of course, but they don't go into much detail on how storage systems operate. And if they do, it's at a higher level, software level, basically. But we will, last time, Mohammed discussed a higher level, but still firmware, hardware, and hardware-software interface level of storage systems, especially flash memory-based storage systems, which is essentially all storage systems today that are really interesting. And today I'm going to go into a deeper dive on the reliability issues based on some of the work that we've been doing for more than a decade, longer than the RowHammer type of research that we've been doing actually. And this is really fascinating because you can discover a lot of new things in this area as well. And this is also another example of research that has actually had a lot of impact in industry. A lot of the ideas, data that we're going to cover are actually ideas that went into flash memory drives to improve the lifetime, to improve the reliability, sometimes to improve the performance and lifetime at the same time. And so you'll see a lot of ideas that actually impacted industry. Relatively faster than what has happened with RowHammer, because in this case, as you have seen in the last lecture, flash memory is a very interesting technology, no problem. But for it to work, you really need to have an intelligent controller, right? Now, if you already have the intelligent controller and an interface for that intelligent controller to manage flash memory, if you have ideas that you come up with that are good, that improve actually some metrics, it's a lot easier to implement them in that intelligent controller because you don't need to change the interface. You don't need to change the flash chips. And you just need to change the firmware and sometimes the hardware to implement those ideas. But that's a lot easier to do if it only touches the controller. In DRAM, we saw that that was not the case. It's not possible to do it just in the controller in many cases because the controller is not intelligent to begin with, right? As we discussed, and we argued for intelligent controllers. So that's the high-level picture that I would like you to take away from it. So there is a memory that's really interesting that was invented in the 1970s, maybe earlier, we don't know. It was first published in the 1970s. And its value, it was an emerging technology for almost 4 decades, if you think about it, flash memory. Toshiba didn't even realize the importance of it. And the person who invented it actually quit Toshiba in the end. Because they were not able to actually capitalize on the goodness of flash memory. It's one of the best storage media that we have invented over many decades as humanity, electronic. You can store things in stones also, if you want. But it's not very fast or very secure either. But again, it actually really took off in 2000s, 2010s with media like music and iPods, for example. And then over time with cell phones or smartphones, you needed to store data, a lot of data. And those SSDs become really important. That's on the mobile end. On the data center end, there was a huge explosion of data. People are thinking about all of the storage, right? Where do you store the videos? Where do you store the AI data that you train on? Anything, basically. That's all on flash memory, a lot of it, of course. There's also tape. Don't forget the other part. There's hard disk, there's tape. So flash memory actually became very, very popular with especially mobile devices to begin with, and over time in the data centers. Today, flash memory has actually replaced a lot of the hard disk infrastructure, which requires on mechanical parts, which are actually fundamentally less reliable than electronic parts. Even though we're going to talk about reliability of electronic parts, always have the big picture. If you have a mechanical part, the reliability of that is actually likely much worse. Okay? Okay, so that's kind of my story to begin with, but I'll tell you some more stories because we've been working in this area for more than a decade now. And this is a paper that we wrote that summarized, invited paper that summarized essentially all of the research that we and some others have done in the field up to that point when we wrote the paper, 2017. This is actually a big reference paper. A lot of people in the field use it. That's true for a lot of the papers actually that we're going to cover, but this actually puts a lot of things together. And I'd recommend you take a look at it. Two people who are authors in this work, Yukai and Yishin, they actually wrote PhD dissertations on this topic on essentially flash memory reliability. And this gives a very good overview. So if you're interested in reading one reference paper, I'd recommend reading this one. It's not up to date. So we actually updated it a few months later with some 3D NAND data. And this is still not up to date. I wanted to update it, but I was too busy, basically, after some point. So a more up-to-date paper and maybe a book remains to be written. But there's also this Inside Solid-State Drives book that actually collects a lot of the articles, including our article over here, that actually has some good introduction to solid-state drives. I don't know if there's an updated version. The last version that I know is from 2018. There's an earlier version from 2010 or so that's a bit older. Do you know if there's an updated version? No, I don't think there's one. Okay, so we're going to cover a lot of things that are actually summarized in these papers. But let's go through some short background on NAND flash memory operation. I'll keep this short because you've seen a lot of it in the last meeting. And you've seen that NAND flash memory has many blocks. And each block consists of many pages, in this case, 256 pages. And we discussed last time that if you want to read operations are done at page granularity. And if you want to read a page, you need to apply a read reference voltage to that page. A page is essentially like, kind of like a DRAM row, if you think about it, right? It's called page in this particular case. Usually not a row in flash memory for some reason, for terminology reasons. But you apply some voltage to that word line to get a read reference voltage. And you need to ensure that all of the other pages in the same block are inhibited from affecting the bit line. So you need to apply a high voltage called pass voltage. So you've seen this last time. So I'm going to go through this relatively quickly again. And if you look at the flash page cell array, it kind of looks like a two-dimensional DRAM array with one fundamental difference. If you look at the cells themselves are actually part of the bit line. It's really a string of cells that are connected to each other, as opposed to that are hanging off the bit line like we have in DRAM. Meaning that whenever you're reading one cell, what's happening here? Oh. Okay, whenever you're reading one cell over here, you need to make sure that the data in the cell propagates to the sense amplifiers without these other cells affecting things. Makes sense, right? That's easy in the case of DRAM because you activate one row, the other rows are not activated by definition. That's how it works. Whereas in this case, if you want to read from this row, you need to apply. You need to ensure that each column passes the data values in the cells that belong to this row. Okay. So you've also seen this sort of picture last time. Basically, this is one cell, and you store data in the cell based on a threshold voltage value of the cell. Basically, you program the voltage in the cell. That's how it works. And there are programming mechanisms like incremental step pulse programming that are relatively reliable on how to set the voltage. You cannot have complete, let's say, control at a very extremely fine level, but you have good enough control to actually set the threshold voltage to say around 2.5 volts. Right? And the amount of voltage or the amount of electrons you put into the floating gate, and you've seen that also last time, right? Determines the value that you program into the flash cell. So based on some threshold, you say, if I have few electrons, a low threshold voltage, I'm going to encode that as 1. If I have a lot of electrons, a high threshold voltage, I'm going to encode it as 0. And usually you have curves where you actually normalize the threshold voltage. We're going to see that. And if your threshold voltage is low, it's programmed as 1. If your threshold voltage is high is programmed as 0. Of course, it could be encoded the other way around also. Right? Encoding is different from what actually happens inside the cells. So let's take a look at how flash read happens. Again, I'll go through this quickly because you've seen it. Assume that you have a cell that's programmed with 2 volts over here, and your read reference voltage is 2.5 volts. If your read reference voltage is 2.5 volts and threshold voltage is 2 volts, then this flash cell passes the value from the top. So you get a 1 in the end. If your threshold voltage is 3 volts and your read reference voltage is 2.5 volts, you apply the read reference voltage to the gate over here, floating gate, and it doesn't pass the value, it inhibits, so you get a 0 at the end. That's how you differentiate between 1 and 0, which was what we have discussed over here, right? That was our encoding of 1 and 0. It could have been easily 0 versus 1. Okay, so that was the read operation for the cell you're trying to read. Now, for the cell you don't want to read, which is belonging to some other row, you want to make sure that they don't affect the bit line. Meaning, if you apply very high voltage to the gate, we call that the pass-through voltage, it will always be greater than whatever threshold voltage you will store. You select the pass-through voltage based on that, and the cell will always pass through whatever value was coming from the top of the bit line. In this case, 1. It could have been encoded as 0 also. Think about that. Okay, so let's take a look at an example read. These are the values that are programmed to 4 pages, each of which have 4 cells. If you want to read from page 2, you apply the read reference voltage, 2.5 volt to page 2. You apply the pass-through voltage to all of the other pages so that they don't affect the reading that happens through the bit line. And this is what you get in the end. So green means pass through, red means inhibit, meaning don't pass through. Which means that because these cells are, threshold voltages of these 2 cells are lower or greater than the read reference voltage that you apply, you get 0 at the end. And here you get 1 at the end because these are smaller than the read reference voltage you apply, and they pass 1, and everybody passes 1 because everybody else is set to V pass equals 5.0, which is greater than any possible voltage that you have programmed any cell with. Make sense? So that's how you read. Clearly, the reading mechanism is different from DRAM, as you have seen. Okay, so there's also NAND versus NOR flash memory. I don't know if we covered this last time, maybe a little bit. Very quickly. We're going to focus a lot on NAND because NAND is high density. What happens with NAND is essentially you have a bit string, essentially what I just described earlier. Cells are hanging off a bit string, so the value that you read is kind of a NAND of the values that you have over there. NOR means that the cells are wired in a way such that you read the or NOR of the values of the cells, which means that there's actually more connections. You can see that there's no bit string anymore where all cells are hanging off. There are partial bit strings that you read from, and you essentially get an OR of the cells. Now, this is much faster reading actually because of the OR as opposed to for NAND to evaluate, you need to evaluate all of these cells. Whereas for OR to evaluate, for one of them to become 1, you get one of them. You just need to read one of them as 1. So basically, this is much faster NAND flash memory. The trade-off is capacity. We always have this capacity latency trade-off in memories, as we have discussed in DRAM, for example, tiered latency DRAM, for example, if you remember. Here, you get much faster reading, but much less density in the cells. And you can see that from this picture, nice picture. So NAND flash memory is used for very high amounts of storage, high capacity storage, where latency is less important. NOR flash memory has not found its usage very well, unfortunately, because it's much less dense compared to NAND flash. Yes, it's much faster, but it's not as fast as DRAM either. So it's one of those memories that some people have banked on. For example, AMD banked on for a long time, but it never materialized. And eventually they sold the business, I think. If I remember correctly, I don't remember the name of the company. I'm too jet lagged. I'm still in, what time is it right now? No, okay, not too bad, I guess. 5 a.m. or something, 5:30, yeah, just waking up. Yeah, basically, NOR flash memory is much less dense. It is also non-volatile, like NAND, but its speed is much faster. But unfortunately, it doesn't come at a nice place in the hierarchy to make a big difference. And it's very expensive. Okay, so NAND flash memory has been the dominant flash memory type. But it's good for you to know that there's NOR flash memory, and it gives you a different trade-off. And its operational principles are quite the same, but it doesn't operate in a bit stream level. Okay, so we've seen the threshold voltage. Normally, what happens in threshold voltage programming, as Mohammed told you last time, is it's not perfect programming. You cannot perfectly adjust the voltage for many reasons, including many things that we're going to discuss today. But one of the reasons is programming is not perfect, for example. So what you get is when you program a cell to, let's say, low threshold voltage or 1, you get a probability density function, probability distribution of where the threshold voltage is. And we usually, this is basically across all of the cells you program, where do they land in terms of the threshold voltage value that you see. Right? You program some of them to 1, and they actually cover a threshold voltage range that looks like this. And this is a distribution function. Basically, most of the cells actually end up to the real threshold voltage that you're trying to program. But based on some distribution, some of them end up here, some of them end up here. Right? Hopefully that makes sense. Similarly, for the other state, this is a single level cell, meaning you store either 1 or 0 in the cell. So because of this, you need to determine a read reference voltage nicely. And you set the read reference voltage so that you can separate the two distributions. Okay. So this is a nice read reference voltage that gives you no errors when you read. Ideally, you set the read reference voltage such that cells that you think you have programmed to 1 will be read as 1, meaning lower than the read reference voltage. They will have threshold voltage values lower than the read reference voltage. And the cells that you think you have programmed to 0 are read as 0, meaning the threshold voltage will be higher than the read reference voltage. In this picture, that's satisfied because the distributions do not overlap. The problem happens when distributions overlap. And that's actually the whole topic of this lecture. What do you do when distributions overlap? How many people have taken statistics classes? Okay. Advanced statistics, basics, Bayesian statistics, frequentist statistics. There's a fight between those guys. I would recommend taking Bayesian statistics. Anyway, I will not go into statistics, but there's a lot of statistical analyses that we will discuss here, but we'll not do in the lecture because a lot of this boils down to statistical analyses in the end. And machine learning, which is a kind of statistical analysis in the end, at least in this current form that is employed in many places. Maybe real machine learning that's going to be a bigger leap for humanity is not going to be as statistics based. Let's see. It's good to think about that also. Okay, so what happens to these distributions if you have multi-level cell? Basically, you have some VTH or a threshold voltage range. You can chop it up into 2, or you can chop it into 4. 4 is multi-level cell. Basically, each cell stores 2 bits. In this case, you distinguish between the distributions using 3 read reference voltages as opposed to a single one. So you program some cells to the erase state. Actually, initially, everything is erased. Remember from the last lecture that you erase at a block level. You erase the entire block for cost reasons. And all cells start from the erase state. Erase state actually has negative voltage. That's why we normally do this, because there's the basic state. And for more detail, you can read papers, etc. And then you program the cells to different values. You can program them to 1, 0, T1 state, program 1 state, 0, 0, program 2 state, 0, 1, program 3 state. And the way you distinguish between the values is apply different read reference voltages. So to distinguish whether or not this is the least significant bit, let's say, or more significant bit, whether or not you're reading 1 at the top bit over here, you apply this voltage, read reference voltage. And if the cell's voltage is lower than that, you know that this bit is 1. Right? Okay, and then you apply this voltage to figure out whether the other bit is 1 or 0. So that's how you read. Hopefully that makes sense. So you can do a binary search essentially. Okay, so normally what we do is like this actually, because the erase state has negative voltage, so you can actually determine what that value is more easily. So you'll see distributions that look like this because we don't normally, when we measure voltages, we don't normally measure the erase state voltage. Okay, this will become more interesting and clear. Okay, here we still have completely non-overlapping distributions. Now, what happens when the distributions overlap a little bit? For some reason, the values shift, either because you couldn't program them well, or because something else happened, like data retention errors happened, or there's some read disturbance that happened. Now, this doesn't look good, clearly. These were the original good voltages that would distinguish between these distributions such that you don't read any cell that you thought to be programmed with in one state to be in another state, meaning you don't read erroneously. If you use the same read reference voltages, if the distributions actually shift, you'll get a lot of errors. We call these row bit errors, basically. You use some read reference voltage, and then these cells that you think were programmed to P3, that were originally programmed to P3, let's say, are now read as belonging to P2, meaning 0, 0. They were originally programmed to be 0, 1, like this, but they shifted for some reason. And now you read them as 0, 0. That sounds bad, right? Now, normally, you should not use the old this voltage, because this voltage assumed that the distributions were not overlapping, right? What should you use? Well, there's also row bit errors over here in a similar way. What should you really use is this, which is where the distributions cross each other. That minimizes the row bit errors, but that doesn't get rid of them clearly. So this the takeaway over here is, if the distributions shift, your threshold voltage also shifts. Your read reference voltage should also shift. So flash controllers do this actually. They are intelligent. They figure out how much the distributions shift, and they actually change the read reference voltages to use to read data such that they can minimize the row bit error rates. Now, you still get row bit errors. What do you do with them? Well, that's what ECC is for. That's what error correcting codes are used in flash controllers, to correct those errors. Yes. We're going to talk about that. Exactly. We're going to basically model these distributions based on some sampling over time. So you can do both, basically. Both are how you do it. In the background, if you probe, you will start with a read reference voltage that's closer to the optimum. That's why it's called optimum. But you may not be able to perfectly get it. So when you read, actually, there's a feature called read retry. We talked about that, I think, last time, or no? Okay, we didn't talk about that. So there's a feature called read retry. If you read and you get some errors, especially if the errors are not correctable by the amount of ECC you have, you change the read reference voltage and retry reading again. And you do that retry until you either get some number of errors that can be corrected by the error correction capability that you have, or you give up at some point, saying that I cannot correct the errors, your flash drive is dead, or something like that. So that's a very good question, basically. Existing flash controllers do both kind of optimization. And the reason to do the background optimization is you want to save time, right? Because if you actually do a lot of read retries, to get the data right from the flash drive, your latency increases. The latency is already large in flash drives. If you want to actually get the data right by doing a lot of read retries, your latency increases. Ideally, you would like to predict the optimum read reference voltage based on what's happening in the flash drive and based on what you're monitoring, so that you never do any read retry. That's the goal. But that's a very tough goal to achieve, actually. You usually do some read retries because you cannot model everything very easily. But we're going to see a lot of innovative, and in my opinion, quite creative techniques to model these distributions so that we can actually minimize the read retries as much as possible. And we're going to see also some techniques that reduce the read retries if you cannot minimize them. And also we're going to see some techniques that try to recover the data, even if you have errors that you cannot correct. So offline, you recover the data from your flash drive, even if you cannot correct them online during operation. All of those are important, right? Clearly. Because there may be some data you may not want to lose. These are not like a million pictures people take. And you lose some bits, in some of the pictures. There may be some really important data that you may not want to lose. Okay, so it's fun. Okay, so how do you program the flash cells? Essentially, if you have 2-bit multi-level cell NAND flash memory, you normally program it using 2-step programming. Initially, all cells are erased. Let's assume that it's 1-1. First, you program the least significant bit. In this case, I'm putting the least significant bit to the left. There's some convention, but I don't like the big endian convention, whatever. You program the least significant bits, like the 1 and 0. And the second bit is not determined yet. Now this is a temporary state. And then you program the most significant bits. So if you want to keep in the 1-1 state, you don't do anything essentially. If you want to go to the 1-0 state, you program the most significant bit with 0, and that's where you go, meaning you increase the threshold voltage that way. And similarly, from the temp state, you go to 0-0 or 0-1. Okay? And these states are actually encoded in a particular way. This is called gray coding. You can see that the consecutive states have only 1 bit changing. That's to make sure that error correcting codes work well. Error correcting codes can detect things more easily if only 1 bit is changing across consecutive states, right? Because only the consecutive states, because of the threshold voltage distribution, can overlap with each other. It's much easier for this state to lose some charge and overlap with this one than this state losing some charge and overlapping with that one. Hopefully that makes sense, right? And we'll see that also. This is also experimentally validated, but also it's intuitively validated. Your errors are such that you actually lose threshold voltage or gain threshold voltage, and your neighboring states overlap with each other much more than non-neighboring states. Okay, that's why the coding is like this. Okay, there are a lot of fun things over here. So this slide I'm going to skip, I think. This is actually a more detailed slide, but so normally you actually divide page sets to even and odd also. And then you have a programming order to program things. But again, you can read the papers for more detail. Maybe what I will mention over here is one thing. So this is what we're doing programming right now, not read. You can see that the program voltage is huge. So whenever you program a flash page, it's actually very energy intensive. 20 volts, that's a lot, you know. I mean, that's reduced a little bit, but it's still a lot. And you need to inhibit everything else while programming that particular page. And you do it incrementally. So it consumes a lot of energy. And also, there is a programming order that you normally follow in which word lines do you program, for example. And that affects the interference between the cells. Because when you're programming one row over here, one page over here, you're affecting the pages below and above, potentially. And the programming order really reduces the interference to only one page, let's say. Okay, we're going to talk about that a little bit more. Okay, so there's also planar versus 3D NAND flash memory. In the past days, all memories were planar, two-dimensional, just like we have DRAM today. All DRAMs are two-dimensional today, actually. Even HBM is two-dimensional. Inside the die is two-dimensional, but then you stack many dice together. That makes it three-dimensional. So we're going to talk a lot about planar NAND flash memory in this lecture. I'm not sure if we'll get to 3D NAND, which is actually the common flash memory today. All the issues that we're going to discuss affect 3D NAND flash memory also. But let me tell you what happened over time. Essentially, planar NAND flash memory, how do you scale it to higher densities? The way we scale any type of memory. You reduce the size of the cell, you reduce the distance between the cells. That's essentially how you make things denser. That's traditional 2D scaling. And that's what DRAM has been doing. Flash memory has been doing it similarly. And flash memory ran into scaling issues much earlier than DRAM ran into. And to increase the, essentially scaling hurts reliability. And we're going to study some of these effects over here. And we did a lot of the early works on, especially scaled planar NAND flash memories, on understanding what are these scaling issues, what are the reliability issues, how do we fix them, how do we make things more reliable, better lifetime, etc. Now, flash manufacturers were also looking into stacking the bit stream in a three-dimensional manner. So bit stream can be planar or bit stream can be three-dimensional. Okay? So if you have a three-dimensional bit stream, what you can do is you can make the cells bigger right now. So you can reduce some of the reliability issues and add more layers on top of each other. today, actually, we're close to 1,000 layers, I think. Are we? Yeah, at least 512 for sure, but I believe we're close to 1,000. Let's see. Maybe it's not out there yet. But basically, you can actually have much bit strings with bigger cells. So that's another way of scaling. So this is what DRAM manufacturers are trying to do right now. You actually have 3D bit strings in DRAM, or in this case, I guess bit lines in DRAM, not bit strings. Can you actually have three-dimensional bit lines that go up the 3 dimension? This is very different from HBM, which has actually bit lines in the planar way, and then you put many dice on top of each other. Whereas you have a true 3-dimensional bit line. And that's essentially what 3D NAND flash memory did. And this was actually a huge breakthrough, which changed the industry. They were able to fabricate this bit string reliably, although we actually studied a lot of reliability issues in that also, which hopefully we'll get to, but that's toward the end of the lecture, you might see. So the reliability of this is not as well studied, but we have some studies at the end of the lecture. But it's good for you to know that whatever affects planar NAND also affects 3D NAND. But 3D NAND initially had a very large cell size, like maybe 3x or 4x the size of the planar NAND. But that's also reducing because the manufacturers have figured out quickly that you cannot add many layers easily, even though you're up to 512 maybe today. Adding more is actually expensive also because from a fabrication process. So they actually are doing both, reducing the cell size as well as trying to add more layers. So that you can scale in both dimensions that way if you have 3D scaling, 3D NAND. Okay, this is what 3D NAND looks like. I kind of showed that with my hands. But these are the bit lines or bit strings, as you can see. And each layer looks like this. So a bit string is over here. This is the flash cell that you have. And this is one type of transistor that you have over here. I will not go through this in detail, but now you can see the source and drain, and the transistors are connected to each other in that bit string. But this is another picture from one of our papers that shows it a bit nicely, maybe. This is bit line 0, bit line 1, bit line n-1. This is at the Z axis, meaning 3-dimensional. And now your word line looks like this. And these are different word lines. Basically, this is your block that we've seen earlier. The only difference is this bit string is vertical as opposed to planar. There's a third dimension based. Okay, and that allowed the manufacturers to make the cells bigger and a little bit farther from each other because they're scaling with number of layers right now. Okay, but again, this doesn't mean that they got rid of all of the reliability issues that we're going to discuss. They're actually coming back much worse right now because they're figuring out the layers are not scaling as well. At some point, there's a limit to number of layers. We don't know what that is yet because there's heating issues also in flash memory. And yeah, we may talk about that also. Okay, so we cover some 3D based memory in this paper, but more in this work. So if you're interested, you can take a look at these. Any questions? So that was kind of a fast background, but maybe not as fast as I thought it would be. Okay, now let's jump into robustness issues. So we were fascinated by the issues that were happening in flash memory. This was, we're talking about 2010 or so, even before we started some of our RowHammer type of research. In fact, our RowHammer type of research was actually inspired by some of what we have seen in flash memory. So we wanted to actually understand where the errors are happening in flash memory. And you've seen this slide before. Basically, in DRAM, you have capacitor charge transistor leakage. In flash, you have floating gate charge and a lot of different type of leakage type of effect. In both cases, you have charge-based memory. And reliable sensing essentially becomes difficult as charge storage unit size reduces. So we're going to focus on the flash memory and what happens when things reduce. This is kind of a summary of the full lecture. Essentially, reliability or endurance of flash storage, which is based on MLC NAND flash memory, is a key challenge for satisfying future storage systems requirements. And we're going to see some of the requirements. Some of them are quite stringent, actually. Our goals in this research was to build reliable error models for NAND flash memory by characterizing real devices. Very similar to what we've done with DRAM, if you have seen the lectures. I mean, many of you have seen the lectures earlier. And based on that understanding that we developed, we wanted to develop efficient techniques to actually improve reliability and endurance, and also performance. Performance is always important. We want to improve things as much as possible without reducing performance. But in some cases, we actually also improve performance because we reduce the read-to-write that we do. So this lecture kind of provides a flash summary of flash memory research over a decade or so. I'm going to go through some of these things. Let's see where we can stop. My guess is we're not going to be able to get to 3D, but who knows? And then there's some other work that is in the backup slide that we're definitely not going to get into. But if you're interested, there is a longer lecture that we can provide a link to, which doesn't have some of these backup slides. Okay, so let's start. This is a slide from, I think, SK Hynix, actually. Yeah, Hynix over there, from 2011 in the Flash Memory Summit. There used to be this Flash Memory Summit, which is called Future of Memory and Storage right now. It was smart of them to actually rename it so that they can actually cater to many technologies. We were the first ones publishing DRAM papers in the Flash Memory Summit, and they were very happy that DRAM folks came to publish there. And now they're Future of Memory and Storage, so yeah, there's actually all kinds of memories. But basically, this picture shows the scaling characteristics around 2011. And you can see that SLC is single level cell, MLC gives you essentially 2x improvement, right? Because SLC, a single cell, stores 1 bit, MLC, a single cell stores 2 bit. And these are the effective cell sizes that you have according to SK Hynix. And these are the sizes that you have in SSDs. So it's actually pretty big. So improvements have been pretty good over time. Now the question was always, can we actually scale to smaller sizes? And what limits the smaller sizes? Essentially the error characteristics. So you go back to robustness, which is really the fundamental thing for scaling. If you cannot make the memory robust in some way, can you scale to lower size? Okay, this is another example. These are all data, but the numbers are actually real. Well, some of these are projected, but they're actually projected really correctly, let's say. So this is another picture that shows what happened to flash memory: single level cell, multiple level cell, and triple level cell. Triple level cell stores actually 3 bits per cell. Okay, that's good. So that's another 2x improvement. And this is an endurance problem that DRAM doesn't have. Meaning, as you write to a cell, you degrade some things in the cell, and you cannot do more writes than writes in flash memory are called programming arrays, as you have seen in the last lecture. I call them writes, but whenever I say writes, think of programming arrays. You need to erase the cell and you need to program it somewhere else. So the number of programs and erases that you do that you can do to a cell is limited, because every time you do a program and erase, remember you're applying huge voltage first, and you're also degrading some of the cell characteristics. And at some point, you cannot write to the cell, you cannot read from the cell, you cannot essentially do anything to the cell. That's called wear out, essentially. The cell wears out over time, and this is also called endurance. So this problem doesn't exist in DRAM as far as we can tell, although Ismail is going to figure out maybe DRAM is an endurance problem and under what conditions that. So this is a good challenge, by the way, as you can see, for people who are doing PhD. This is a discovery, in my opinion, if it happens. It may not easily happen. But if you discover something like this, it's huge. Okay, anyway, but flash memory has this from the get-go. And you can see that if you store single level cell, the programming erase cycles is on the order of 10, I don't know, 100,000, maybe 50,000 or 40,000, 30,000. If you do multi-level cell, it's about a 3,000 or so. If you do triple level cell, it's actually close to 500. And actually in future generations, close to 100, which is crazy. You actually can do only 100 writes to a cell before the cell dies. Make sense? Not good, of course. Yes. No, you can actually do quadruple. Basically, you have a voltage range, you can chop it into as small as possible. But as you chop into more intervals, meaning store more cells per bit, your reliability and endurance problems become much worse. Yeah. Today you have quadruple level cells, QLCs. You can do that also, yeah. Say it again. I see. Yeah, you can. Maybe I didn't quite understand that, but yes, you can combine things. I agree. Yes, you can combine SLC and MLC in different parts of a flash drive. No problem. Yes, because what you're doing is in the end, you're deciding how do you chop up the voltage range for a given block, for example. You cannot do it within. Actually, I haven't thought if you want to do it within a single block, but on a per block basis, you can do it easily. Yeah, yeah, you can actually play tricks, as you said, to achieve a good density or capacity while also achieving some good reliability, right? And you can also switch. Like if you think that, or you don't need that much capacity, but you need more endurance, then you can switch from TLC to MLC, for example. All of these are possible with your controller. You can customize your controller. You can program your controller. These are all programmable controllers, as you've seen in the last lecture. Yeah, you can adapt these. There's a lot of potential for innovation. Yeah, and there are papers that propose things like that. But for your specific idea, talk to us afterwards, because it requires some thinking. Okay, so basically, you can see that if you want MLC, for example, the program and erase cycles that you have provided by the fundamental characteristics of the device is about a few thousand. But some storage requirements dictated by industry or some use cases actually require much more than that, meaning more than 50,000 program and erase cycles, for example. This assumes some worst case conditions, like writing the full capacity of the drive 10 times per day for 5 years. That's a goal. Of course, people don't do that, right? But maybe there are some people who do that, right? It's good to think about that. This requires 50,000 PE cycles. Okay, even if you don't do this, maybe you require 10,000 PE cycles and you require high capacity. And high capacity requires TLC, maybe. And you basically have 300 versus 10K, and there's a big disparity between those. So basically, fundamentally, the device has very small PE cycles that it provides. But at the system level, you want actually much larger PE cycles. So how do you bridge that big gap? And this talk is actually about bridging that big gap as much as possible. Okay, so this is another picture, actually. I like this kind of pictures sometimes. It's good to motivate. So endurance decreases with flash scaling, right? This is actually very similar to what we have seen earlier. This is 2x MLC, this is 3-bit. With multi-level cell, endurance is decreasing. Let's assume that you actually have storage class reliability that you want to guarantee. Let's say that you want an uncorrectable bit error rate that's less than 10 to the minus 15. That's a rate of errors that you get whenever you do some reading. And 10 to the minus 15 is pretty stringent, actually. And if you want to correct all of the errors with error correcting codes, you need actually much stronger ECC. So your ECC needs to increase exponentially in terms of area, hardware area, to actually reach less endurance. So that's the problem, basically. You get higher capacity, and higher capacity gets you less endurance, and you get errors. To correct the errors that you get at higher capacities, you need much larger ECCs. So you pay cost for ECC and you pay cost for wear out as well. And the cost of endurance is actually not good, because if a cell stops working, what do? Well, you've seen in the last lecture that you may over provision your space. Right? You actually sell a 1 gigabyte drive that actually has 4 gigabytes in it. Well, we should talk about terabytes actually today. 1 terabyte drive that is actually 4 terabytes. And you use the remaining 3 terabytes to act for intelligent management, right? To make sure that your cells don't die. Or you have DRAM that's added to the SSD drive, such that whenever you write to DRAM as much as possible, and you don't write to your flash memory as much as possible. That way you get rid of a lot of the wear out that you may have to do if you didn't have DRAM. So the system level techniques can actually reduce things, reduce the issues related to wear out. And we've seen some of those. Today, we're going to look at the error characteristics and actually how to try to solve them as much as possible. So what are these errors basically? Like, where are these errors coming from? I like this picture because this picture shows a communication channel. And I think we should be thinking of memories as communication channels also. And it's a communication channel, right? You communicate through a storage device. you have this NAND device, you write data, which is what you want to communicate. And then at some point, somebody reads data, which is the receiver. You transmit by writes, you receive by reads, essentially. And during that communication process, you actually have a lot of noise. And all of that noise is dependent on what kind of errors you have. Right? So basically, there's noisy stuff that's happening. Ideally, we would like uncorrectable bit error rates. This is the system level requirement. That's less than 10 to the minus 15. This is also called Uber. There's also arbor, which is raw bit error rate that you get when you read from the device. And then to achieve the uncorrectable bit error rate, you need to do some other things, right, at the system level. This is what the controller may do. So error correction, for example, may come into play, but other things may come into play. So we're going to talk about a lot of memory signal processing techniques. I like thinking of them as signal processing, but error correction may also go into it. But I will not argue what is error correction, what is signal processing, because at some level, error correction is also signal processing. And Reed-Solomon codes are error correcting codes, by the way. Okay. Anyway, that was a joke that we can talk about later. But basically, some people at Google think Reed-Solomon codes apparently are not error correcting codes. But maybe they should take our classes. Okay. Maybe they'll listen to this lecture and figure out. Okay. Anyway, but basically, you get some data, you process the signals, you minimize the raw bit error rate as much as possible. But even then, it may be high. And then you apply some error correction techniques to hopefully reach an uncorrectable bit error rate that's a system level requirement. And we're going to try hard to reach that. So ideally, you would like the raw rate to be as low as possible. And you would like your error correction capability as better as possible without adding a lot of logic. So our goal is really to build reliable error models for NAND flash memory such that we can achieve those efficient reliability mechanisms based on the models. So let's take a look at the errors that you can get. We're going to see some of these. Basically, you get errors all the time in this communication channel. It's good to also think about other memories like this. I haven't seen as much like work in DRAM, for example, that model DRAM, but I think there's a good opportunity for that. And Ismail, again, has an opportunity over there. But he's not thinking about eating sushi in Japan. Okay, so whenever you write, essentially, you want to experimentally characterize and model dominant errors. And this is the original paper that we have looked at. So when you write, for example, you get errors when you're erasing a block. Erase is not perfect. When you program a page, that's not perfect. You may get errors. So these are erroneous things. And we have characterized some of these. I'm not going to talk about everything, but some of the things we're going to talk about. So that's write process. Write process is not perfect. And then when the block is sitting over there, you're not doing anything to the block, it still gets errors. Why? Because you're doing something to the neighboring pages, or I should say pages sitting there. You're not doing anything to the page. You're doing something to the neighboring pages. And as a result, you get errors because of cell-to-cell interference and program that's happening in neighboring pages. This is very similar to read disturb errors or program interference errors. Okay. And even if you're doing nothing to the adjacent pages, you still get errors. Why? Because you lose data. This is charge-based memory, and it cannot retain charge. There's leakage that's happening. Maybe not at the same scale as DRAM, but it's still happening. So you lose data. So you can see that between when you transmit the data and when you receive the data, or when you write and read, you're subject to a lot of noise. And the question is, can you model this noise in an intelligent way such that you minimize the errors that you get on the receiver side, while of course optimizing for high performance and also low hardware cost at the same time. Okay, so we've actually written a lot of papers, as you can see. This is not the comprehensive list, but these actually deal with different parts, and some of the papers actually deal with all of the types of errors at the same time. And this paper that I showed you, that is a summary paper that it covers everything actually, including some new data. So let's take a look at, I've already said this, so I'll go through this relatively quickly, but we want understanding and we want developing efficient error management techniques. So our approach has always been develops solid experimental analyses to drive the understanding and modeling. And based on that, plus creativity, come up with new techniques. I cannot, I think these need to be combined basically. You got to develop understanding, you got to do modeling, and you need to have some creativity. And I believe some of these ideas that we're going to discuss are going to have some nice level of creativity in them, because you need to see what's inside the distributions, for example. Okay, so this is a summary of the types of errors that we're going to look at. So this is the error type over here. This is the mitigation mechanism. This is from the paper that I mentioned. There's program in erase cycling, there's program interference, there's self-cell interference, there's data retention, there's read disturb, and there's probably more that is not covered in this case, especially with three-dimensional flash memory. And if you want, this paper has a lot more. Now let me go into how we did this characterization. So basically, we use an FPGA-based platform, very similar to the DRAM vendor. It was never open source because we worked with companies that actually helped us develop this, that had also interest in understanding these errors because they were actually building some of the fastest storage controllers, SSD controllers at the time. It's not easy to develop this sort of thing without some insider information. So we're very grateful for people actually who worked with us to enable this sort of information to be public. So you need actually some, not the infrastructure necessarily, but the information. So there was very little information when we started on the error characteristics of state-of-the-art flash memory chips. There were some papers here and there. There are device-level papers that don't mean much from an existing device scale or modeling scale. You cannot model based on device-level papers because they look at a single cell, for example, and they look at the reliability of the single cell. We want to look at the reliability of billions of cells so that we can understand what's going on and model, right? So the collaboration with LSI Logic and then Seagate has enabled actually a lot of data to become public and a lot of techniques to become public over time. And initially, when we started this research, we were behind industry, meaning industry knew a lot more because academia knew almost nothing. Nothing was published, you know. But once we actually started this research, we started learning. And because we can move much faster, because we're not designing products, right? Our goal is to actually understand and model and design the much better future. We actually surpassed what industry knew, and industry actually adopted a lot of the techniques that we have come up with over time. That's the beauty of doing research, essentially. But also in an area like this, you need good partners. And this is an example of where some industry can actually enable good research. I wish the manufacturers actually did this also, but hopefully they're listening. Yeah, manufacturers don't do this. That's unfortunate, but that's how it is. Okay, so we looked at 4 types of errors in our original paper. These are caused by common flash operations, read errors, erase errors, program interference errors. And one of these is caused by flash cell losing charge over time, the retention errors essentially. Whether an error happens depends on the required retention time, of course, right? Retention is always dependent on the time. How long do you want to retain data? If I store something on my cell phone, or worse yet, a USB flash drive, which is some of the lowest quality flash chips go into the USB flash drives. So don't trust those. And if you want to retain data over there for 10 years, good luck. That's a very long retention time. And especially if you expose this USB to interesting conditions like 70 degrees Celsius or whatever, it can happen if you leave your USB drive in a car in the heat of the Death Valley, for example. If you've been to Death Valley, you probably know what I'm talking about. That's where actually they do a lot of robustness testing of cars, by the way. Death Valley in California. They should do more robustness testing of DRAMs also, perhaps over there. Ismail, that's your next destination. No more Japan. Death Valley. I'm just kidding. Actually, you were close by, weren't you? Like you were in Dallas. Actually, not that close. Okay, fine. Okay. Anyway, basically retention time. Retention errors depend on how long you want to retain data. 2 hours is a lot easier than 10 years. And we will see that actually also in the results. And this becomes especially programmatic because threshold voltage window to determine stored value is smaller, as we have seen. Voltages, threshold voltage ranges become closer to each other and sometimes overlap, as we will see. So basically, we developed usage and error models. So whenever you, this is for a given block, you start and you program and erase the block, that's cycle 0. And you do another program and erase, another program and erase, another program and erase. And eventually, you cannot read, write, or do anything to the page. In this case, let's call it a page over here. And that is basically when we declare the page dead. You cannot do anything. But then when you do an erase, there are some erasers that you get that you can characterize. those errors. When you program a page, there are program errors that you get, and you can characterize that. And then you can actually test for different levels of retention: hours, days, years. Years testing is a bit more tricky. So we're going to bake the flash chips to actually accelerate aging. And then you also, whenever you're reading, you get read errors that are different from retention errors. So you need to classify them. And we have a methodology for classifying them. And then you have different type of retention errors based on the retention age. So this is our methodology. I'll go through this relatively quickly. But at the time, these were the state-of-the-art chips. Today, we're at 1x, 1y, very low nanometers, basically. And we quantify the row bit error rate at a given program in erase cycle. So you program in erase and program in erase, and you look at the row bit error rate at that usage level or at that wear out level of a given cell. I think row bit error rate, we've discussed what that is: fraction of erroneous bit without any correction. And then we quantify the error correction capability and the area and power consumption of various BCH codes. It's hard to remember the names of these guys, but those I remember. That's easy. Ismail, do you remember? Okay. Then Death Valley. No, yeah, you picked Death Valley over Japan. You know, Death Valley can be great, actually. It's a very unique place in the world. Okay. And then we identified how much row bit error rate each code can tolerate. So BCH is actually one type of error correction code. There are many, many types of error correction codes, initially starting with Hamming codes. And many people over time invented different types of strengths of error correction code. BCH is one example. Usually they're named based on people who invented them. Both. Come on, somebody can do it. You know, this is when we need AI. Yes, Rakesh. Chowdhury? Okay, good. Okay. You guys are still not using AI. This is where AI could be useful, you know. Okay, but good, thanks. And then there's Reed-Solomon, for example, that I remember, RS codes. And then there's more recently, if you read the paper that I mentioned, there's low density parity check. That does some soft decoding, hard decoding. Again, we're not going through error correction theory over here. There should be other courses on that, hopefully. But essentially, we looked at various strength of error correction code implementation and see if they can actually correct these errors that we have seen. And how many programming erase cycles each different error correction code can sustain. And that's called flash lifetime, basically, which programming erase cycles you get. So flash lifetime is determined by the number of programming erase cycles at which you get an uncorrectable error, right? Given clearly the flash memory and also the error correction code you have. So it's a function of error correction code as well. Okay, so let's take a look at some of these results. I think I'll go through this relatively quickly also, but basically you need to basically know what you're doing. You need to come up with a methodology like we have done in DRAM. For example, for erasers, you count the number of cells that fail to be erased to 1 month state. If you cannot set a cell to 1 month state when you're erasing, clearly you get an eraser. You program interference errors, you compare the data immediately after programming a page and the data after the whole block is programmed and see if they match. Read errors, you continuously read a given block and compare the data between consecutive read sequences. Retention errors are a bit harder. Compare the data read after an amount of time to the data written, after the data was written. You can characterize short-term retention errors under room temperature. That's what we do. But we characterize long-term retention errors by baking in the oven under a large number of degrees centigrade, as you can see. This is based on the Arrhenius equation, which was developed by Arrhenius. That I can pronounce kind of. But essentially, this is a Danish scientist, Danish physicist, actually. Right? Am I correct? This is where AI can be useful also, you know, it can help us, but we're not there yet. But basically, there's a relationship between data retention or leakage, more appropriately, data leakage and temperature. And we've seen that data leakage and temperature depends on DRAM. It's very much there in flash memory also. So by changing the temperature, you can accelerate kind of retention age. Okay, so these are some real data from real devices. This was this was our original paper, actually. If you look at the programming erase cycles, it goes from 10 to the power of 2 to 10 to the power of 5 over here and more. And you can see different types of errors over here. So these are, for example, this is on the x-axis, on the y-axis, you have row bit error rate. So how to read this? Basically, if you are working with a page that is a 10 to the power of 4 programming erase cycle, you've done 10 to the 4 programming erases, this is the robit error rate you get for erase errors for that page. This is the robit error rate you get for read errors. Now you can see the numbers around 10 to the minus 7, 10 to the minus 6. Right? And then yellow one is 1 day retention errors. You read the data after 1 day. Not too bad, as you can see. And then the purple one over here, purplish pink, violet, that's 3 day retention errors. So you can see that these errors are close to each other at 10 to the 4, if that's your goal. But now if you look at all of the errors over here, these are long-term retention errors. With 3 weeks, 3 months, 1 year, 3 years. Basically, retention errors dominate, because you can see that this is 10 to the minus 2 over here. You go to 10 to the 5. So basically, robit error rate increases exponentially with P cycles, regardless of the errors, maybe except for the erase errors. That's not as bad. But retention errors are dominant. So not more than 99% of the errors for 1 year retention time are actually retention errors, essentially. And retention errors increase with the retention time required. So we basically said that the key areas to handle are retention errors. These are early days of MLC flash memory. iPhones are just getting popular, maybe. Right. So basically, our target was to fix the retention error problem. And we're going to talk about that next. So what is the retention error mechanism, actually? Then we basically said, this paper has a lot more analysis, actually, but I'm not going to go into that. I just want to talk about retention a little bit, and then we're going to move to other errors. But then we're going to go back to retention, because retention becomes much worse again. So essentially, you lose electrons from the floating gate. Very similar to you lose electrons from the capacitor in DRAM. And cells with more programmed electrons actually suffer more from retention errors. That's what we found empirically. And threshold voltage is more likely to shift by one window than by multiple windows. So I basically have some stress-induced leakage current. And this is what happens essentially. Distributions shift to the left. And the distributions that have more self-programmed into them shift more. This is kind of a pictorial depiction of it. Okay. This is also dependent on values that you store, which is interesting, and values are around you. Very similar to data pattern dependency that we have in DRAM. You don't need to understand this graph because I'm not going to explain it. But cells with more programmed electrons tend to suffer more from retention noise also. Okay, there's more in this paper. Now let's take a look at how we can correct it, and then we're going to take a break. So how do you solve this problem? Basically, we know how to solve this problem in DRAM, right? Refresh. The same solution applies here. But then refreshing can take multiple forms in flash memory. In DRAM, there's only one way of refreshing. Actually, in DRAM, you can do the same thing. Sorry. But people don't do it in general. So refresh periodically, basically. Change the period. Okay, you can be more smarter. Instead of having a period that is very frequent, you change the period based on the wear out of the page. How many programming erase cycles I have done. Now, if you have listened to the last lecture, you do vary leveling. So hopefully all of the pages have similar wear out levels. Right, Mohammed? You do vary leveling, so hopefully all of your pages have similar wear out levels. So you can do this not on a per block basis, hopefully, but who knows? If your wear leveling mechanism is not that good, you may need to do it on a per block or per page basis. But this is adaptive refresh, basically. Okay, refresh more often at higher programming erase cycles. So when the flash memory is not written to at all, you don't refresh it at all. When the flash memory is written 1,100 times, maybe you refresh it every 3 months. When the flash memory is written 1,000 times per block, maybe you refresh it every 3 weeks. 10,000 times, maybe you refresh it every 1 week or whatever, right? You determine it based on some empirical data that you collect based on the characterization. When you're written 50,000 times, you refresh it every hour. I just made up those things, but they're close to reality. Right? So that's the idea, basically. It's not every 64 milliseconds. And here we use a combination of in-place and remapping-based refresh. In DRAM, for example, we do in-place refresh. Right? You replenish the charge. You can do the same thing in Flash, but if you do that thing, you run into some program errors. So sometimes you may want to remap the data to some other location, some other block, so that it starts fresh. Okay, this is described in the next paper. that we presented at ICCD, which is implemented in a lot of flash drives, actually. Essentially, the observations are retention errors are the dominant source. We have discussed that. They limit flash lifetime as they increase over time. And retention errors can be corrected by refreshing each flash page periodically. The key idea is to periodically read each flash page, correct its errors using some weak error correcting codes that you have, and then either remap it to a new physical page or reprogram it in place based on how many errors that you have, that you think you have based on programming. Of course, you do this before the page accumulates more errors than correctable by the error correcting codes that you have. So you can also adapt the refresh rate to endure P cycles, how many programming erase cycles that you have done. So it's a full mechanism that incorporates all of these. But there are two key questions essentially. How do you refresh? You can remap, you can reprogram, or you can have a hybrid of remap and reprogram. We choose the hybrid because remapping is expensive, right? You move the page from this block to this other block. You need to read the entire page. You need to copy it to some other block. You need to change the translation table that maps the logical to physical pages, right? Then maybe you need to actually trigger garbage collection while you're doing all of that. We discussed that last time, so I'm not going to go into garbage collection. But basically, remapping can be expensive. Reprogramming in place is easy. The page has some errors, you just replace the chart so that you don't have errors, hopefully. And then there's a when to refresh part. Do you do it fixed period? Do you adapt the period to retention error severity? We choose adapting the period. So it's an optimized refresh mechanism. It's not a dumb refresh mechanism because you could easily do a dumb refresh mechanism like DRAM, but that'd be terribly boring. Okay, so let's take a look at in-place reprogramming. So this is the voltage distribution of each stored value that we have seen. And retention errors are caused by cell voltage shifting to the left, as we have seen also. We just want to shift them to the right so that hopefully they get back to where they were. Of course, this is ideal. So the good news is incremental step pulse programming, which is the mechanism to program flash cells, always move the voltages to the right, meaning they increase the charge level in the cell. So they are great for, it's great for fixing retention errors. So you basically add more charge. So the program, the pro of this is no remapping is needed. No additional erase operations you trigger. That's great. But there's a downside, like everything. You increase the occurrence of program errors because you're programming in place. So you want to do this until you get too many program errors than correctable by the error correcting codes you have. That's the idea. Okay, so the problem with in-place programming, you basically inject additional electrons. And while you inject additional electrons and you change the read reference voltage, let's say, this is your original data to be programmed. And then you get some program errors after initial programming. And then you get retention errors after some time. Red ones are retention errors, blue ones are program errors. You correct the retention errors. You read the data, correct the errors, reprogram back in place. Now you get another program error potentially, which you may not be able to correct. Maybe you're going to correct this because your ECC may be powerful enough, but over time, these program errors may accumulate. Okay, that's the idea basically. Okay, so adaptive rate, we've already discussed this. Retention error rate strongly depends on the programming erase cycles the flash page has endured so far. You don't need to frequently refresh early in flash lifetime. So you adapt the refresh rate to the programming erase cycles endured by each page and increase refresh rate gradually with increasing P cycles. So this reduces the overhead of refresh operations, which we're also going to quantify. Energy is also important here, by the way. And you can use existing mechanisms. So all of these can be done in existing FTL, fast translation layer. You can keep track of the program erase cycles, for example, per page. So this is an example. This is actually based on real data that we have, programming erase cycles. These are the retention errors, 3 day, 3 week, 3 month, 3 year. This is the beginning of flash lifetime. And you have a robot error rate. And normally the way you do these analyses is you have some error correcting code budget that is capable of correcting a robot error rate of some value, which is 10 to the minus 4 in this particular case. So if you have 512-bit BCH with some implementation, you can correct 10 to the minus 4 robot error rate, which is clearly much higher than anything until this point. Right? So until programming erase cycles over here, you do a 3-year refresh. You refresh the flash for 3 years, every 3 years. That's what I mentioned earlier. Now, at some, to retain the data for at least 3 years, you need to refresh. Meaning, after that point, after this, whatever this programming erase cycles is, until this point, you need to increase your refresh rate so that you can retain the data for 3 months. So you refresh the flash for 3 months, every 3 months. Hopefully that makes sense, right? Because you need to retain the data that would otherwise get errors if you don't refresh. Make sense? And here again, this is the 3-month errors. You could of course have more data and refine this to 1 year or 2 years, 1 year, 1.5 years, whatever. But we didn't have data. We looked at the data for 3 years, 3 months, 3 weeks, 3 days in this particular case. And then you're in a regime where you have corrected, you didn't get errors in this part. And once you go into the next regime over here, you refresh the flash every 3 weeks. That's the cycles that are in between this interval. And once you go into the next regime, you refresh the flash every 3 days so that you retain data. And then you refresh the flash more often. That's the idea basically. And you select the refresh frequency based on your data such that the error rate is below some acceptable rates. Assuming you're doing modeling or you're gathering this experimental data under worst case conditions. That's the key, right? And then you can adapt this to temperature also, like we have done in DRAM. Okay. Okay, so if you do all of these techniques, it turns out these are actually some very powerful techniques to begin with. If you don't do refresh, your lifetime is very low. If you do remapping by refresh, you actually improve your lifetime, which is great. If you do a hybrid flash correct and refresh, you increase your lifetime even more. And if you do adaptive refresh on top of hybrids, that's the best. So it provides the highest lifetime. If you use low error correcting codes, 512 bits, low capability, your lifetime increases by 46x, for example. And lifetime of doing this refresh is much higher than the lifetime of strong ECC. So if you only use ECC and not do some sort of refresh, going from 512 bits BCH code to 32K BCH code, which is extremely expensive, buys you only 4x. Here we get 46x without changing the error correcting code. This is another example of why ECC is a bad idea when you know the reason why errors are happening. Somebody should tell this to Micron. I think they figured it out. But basically, this is real data from 2012 that says, don't correct retention errors with ECC because you have a much better way of doing that, which is what we propose. Okay, so hopefully this is actually interesting data. Sometimes industry should read papers more. Actually, the storage industry reads these papers more. These papers are taught in SSD controller, flash memory, device manufacturers, as well as controller manufacturers. They actually use this as learning material. A lot of people come to me and say, oh, I learned, I started work at company X, and I learned about how they design their products from your papers and how to do better based on that. So this is actually, I think, an accomplishment that we have as professors. Even though we get paid a lot less than these folks at companies, we provide a lot of material that hopefully is useful for them to build better products. Yes? Even for DRAM. Oh, even for DRAM? Okay, that's good to know. I think I heard that also, yes. Okay, so energy overhead. Clearly, whenever you do a refresh, you have energy overheads. But if your refresh interval is 1 year, your energy overhead is negligible. 3 months, also negligible. 3 weeks, now it becomes less negligible. 3 days, 1 day, clearly you can see the energy overhead increases basically. So if you do adaptive refresh, you get 1.8% energy increase until daily refresh is triggered. And daily refresh. So this is also another way of thinking about this is you're pushing your flash memory to the limits if you're refreshing it daily, right? Because your program erase cycles are very high at that point. Maybe unacceptably high even at that point. But your energy overhead increases when your flash memory is actually closer to the end of its lifetime. Maybe you should be thinking about replacing some of your flash memories at that point, right? Because you're using it too much. It's good to think about it that way. Okay, so this is the paper, flash correct and refresh, and it has a lot of impact on industry. But we're going to talk about, there's actually another paper based on the work that we've done. We were invited to write a paper to the Intel Technology Journal. They had a special issue on memory resiliency in 2013. And we summarized some of the work that we have done, which was very little at the time, but it was actually very important. So we covered some of the work on this Intel Technology Journal. And Intel used to actually manufacture NAND flash at that time. They sold out that business after some number of years. They should have turned into a memory company, in my opinion, as opposed to struggling like what they're doing right now. They could have used some of the other things in a better way, basically. But anyway, okay. Okay, this is a good place to take a break. Let's take a break for, I guess, 15 minutes. Let's be back at 2:46. Now we're going to cover even more fascinating things, more difficult to correct errors. Okay, let's get started. So now we've looked at retention errors. We're going to come back to them. But there are many other errors, as you discussed. Let's see how many of them we can cover. And earlier you asked for how do we determine how do these threshold voltage distributions shift? And we're going to look at that now. And we're going to look at predicting read reference voltages before they shift by doing some analyses on experimental characterization data. And then we're going to look at some really innovative mechanism, neighbor-assisted error correction. And all of these are, again, implemented in real flash controllers and more sophisticated mechanisms these days, actually. And then if we have time, we're going to talk about read disturb, more retention error handling. Let's see how much we can cover. There are a lot of interesting things over here. And then there's a 3D aspect of all of these, which we're probably not going to get into, but I will probably flash some papers at the end, or maybe tomorrow, before we move to some other topic. So this is a fascinating area, basically. There needs to be more that needs to be done in this area. Okay, so let's go back to these threshold voltage distributions. Essentially, there are several key questions here. How does the threshold voltage or VTH distribution of different program states change over flash lifetime? Can we model it accurately and predict these VTH changes? And can we build mechanisms that can correct for the VTH changes, thereby reducing read error rates? So these are threshold voltages that are measured from many flash chips at the time, using the read retry feature that we discussed. You read, retry. If you get errors, you retry again. But basically, you can map out the probability density function of these different states, program states, P1 state, P2 state, P3 state, under different program and erase cycles. So this blue one that's at the peak over here is 1K cycles. So flash is not used that much, let's say. If you have 3K, the distribution is the green one, and then 8K is the yellow one, and then 15K is the red one. You can see that shifting to the right and also widening. So the threshold voltage distribution of different program states, essentially as PE cycles increase, the distribution shifts to the right and the distribution becomes wider, which is interesting, which means that you can model it, assuming you can fit some sort of distribution to it, right? This is where the statistical analysis comes into play. And what we did in this work is we were able to model it with some Gaussian distribution with some additive white noise, which means that you can predict the shifts. Okay. So with some accuracy, 95%, as you can see, we found out that you can model this as Gaussian distribution with additive white noise. And the distortion in VTH over programming erase cycles can also be modeled and predicted as an exponential function of programming erase cycles. For that, you need to read the paper more, but essentially you can model and predict it based on the number of PE cycles that you have. Again, with more than 95% accuracy over here. And that's this paper, okay? There's a lot of analysis in this paper that I'm not going through. The issue is these distributions hold for specific devices. So this was for, I think, 2Y nanometer. Yeah, 2Y nanometer, like 25 to 29 nanometer feature size flash chips. Now, if you go to smaller flash chips, we found out that these distributions are actually much harder to model. And this is a paper that you can see. It's in the selected areas and communications. It's in a communications journal because they do care about channel modeling. And you can see these are real distributions for really dense chips, 1x nanometer. 1x is basically 10 to 14 nanometer, which is essentially less than half the feature size of what we've tested earlier.
And you can see these distributions over here. If you actually use a Gaussian-based model, the data points are, the distributions that try to fit the data points are dashed lines or solid lines. The data points are actually points. And you can see that when you try to fit a Gaussian distribution, it doesn't fit over here. There's some really interesting pieces of programmed value 1 distribution that happen to be over here. And the distribution overlap hugely. So this is the scaling problem that you have at hand, basically. When you go from, this is 2y nanometers, you can see that overlap of the P1, P2, P3 distributions are not that bad. There is overlap, no question about that. You can see that there's a long tail over here that's overlapping with this pink distribution over here, right? There is overlap, but the overlap becomes much worse when you go to 1x nanometers, right? This is the scaling problem, because you reduced the distance between the cells and you reduce the cell sizes. And Gaussian distribution doesn't work very well. In fact, some of the cells from P1 overlap with P3. So multiple distributions overlap with each other also. So how do you correct the values becomes much harder with much smaller densities or much smaller feature sizes. So we basically try to correct this. So we actually now develop a student's T-based model, which actually tracks the distributions much better, as you can see. This is the dashed value. A Gaussian distribution wouldn't be able to track this, but this T-based model actually tracks this nicely. It also tracks this nicely. Still, there are some errors, but they're much better than the Gaussian distribution. You can see that we can track this also nicely. Okay. So we looked at different distributions to fit the graphs, and we can reduce the modeling error significantly compared to a Gaussian distribution. So you need to basically model it nicely if you want to predict what kind of read reference voltage you're going to use. Okay, so this is prediction versus reality with better modeling. So essentially here, we predict the threshold voltage distribution for 20K PE cycles based on characterization data from earlier PE cycles. These predicted distributions are shown as dashed lines over here. And markers are data measured from real flash chips at 20K PE cycles. So we're not too bad, as you can see. But you can see that the flash channel is quite messy. So there's a lot of overlap. This is P2 overlapping with ER. Even the erase state is not erased anymore. That looks interesting, right? So that's why actually manufacturers went into 3D. And we have a planar, this planar flash has not scaled beyond 1x further. And manufacturers, when they went to 3D, they went to, I believe, 3x to 3y nanometers, which is 30 to 39 nanometers. In the end, they increase the size of the cell so that they don't need to deal with this mess that you're seeing in this picture. And this picture is really a mess. Okay, anyway, you can read, there's a lot of actually discussion and analyses in this paper. Yeah. I think one thing maybe, anyway, maybe I'll throw it out, but there needs to be more work in this area. But in my opinion, machine learning can be actually good to put to good use in this sort of modeling systems. Here, we're actually using modeling based on our own intuition and our own mechanisms. But maybe with machine learning, you can model things much better. An idea. Okay, let's talk about program interference. This is another type of error. When you program a cell, the voltage level of a neighboring cell changes unintentionally due to capacitance coupling that happens. And this can change the data value that's stored in the neighboring cell. This is also called program interference error. And essentially, this causes the neighboring cell voltage to increase, meaning shift right. Right? It's very different from retention, right? Retention shifts left, reduces the voltage of the cell that's subject to the error. Here, you're changing the voltage of a neighboring cell, increasing the voltage. And it turns out once retention errors are minimized by doing smart refresh mechanisms that we have discussed, program interference can become dominant. That's why we looked at this in more detail. And you've seen this picture, basically. We program MLC NAND flash cells using two-step programming. This also says that the latency of programming 2 bits per cell is larger than the latency of programming 1 bit per cell. So again, another latency capacity trade-off. But you've seen that also in emerging memory technologies when we covered phase change memory. So let's take a look at program interference. So let's take this is actually very similar to disturbance error, but this is more like a write disturbance error. You're writing programming and you're disturbing adjacent cells. Let's assume that this is our victim cell, that you want to model the interference happening to it. These are the cells that can cause interference. There could be others, of course, also. But assume that these are the voltage changes that happen in physically adjacent cells. So we can model the voltage change that happens on the victim cells based on the voltage changes that happen in the physically adjacent cells. And you can do this because we can actually measure these voltage changes using our flash infrastructure. Now, this is very difficult to do in DRAM. If you can do it in DRAM, that's great, but we cannot measure the voltage values or the capacitance values in the capacitors, right? Although Ismail may change that, who knows? I'm picking on Ismail today because he's thinking a lot of good ideas, I think. Okay. That's what happens if you do good work. No good deed goes unpunished. More good deed is expected from you. But you do get to travel to Japan and a lot of places also. That's the good part. See, I'm a bit jealous that he's traveling to Japan and I haven't traveled. Okay, instead we get this beautiful snow. Although Japan gets really beautiful snow. Were you in Hokkaido? Okay. Hokkaido is good. What? Next time, okay, yeah. You got to pick a good conference in Hokkaido then. Have you read any Haruki Murakami novels? Does anybody know Haruki Murakami? Okay, there you go. He has good stories about Hokkaido and many other places. Anyway, let's go back to Flash. But it's good to read Haruki Murakami also, or anyone who writes well. Okay, basically, we're going to model the voltage change that happens to victim cell based on the voltage changes that happen to adjacent cells. We're going to ignore the bottom part because, as I said, there's a program order you follow in Flash. And if you program this word line before you program this word line is not going to affect this word line. Right? And Flash manufacturers, as we discussed in some of the papers, including this one, actually follow some program order that tries to minimize noise. We're not going to talk about that. But because of the programming order, the bottom word line 0, is not going to affect the victim cell. But the other parts, whenever you program word line 1, the adjacent cells are going to affect the victim cell. And whenever you program word line 2 after word line 1 is programmed, the adjacent cells will affect the victim cell. And whenever you program word line 3, that could also affect the victim cell in word line 1. Right? So there were people who had developed models for this. And this was a particular model. So you can model the victim cell's threshold voltage change as a function of the voltage change that happens in X parts 2 times, because there are 2 of them, and the capacitance, coupling capacitance, which is very difficult to know, plus voltage change that happens at the immediate upper neighbor times the coupling capacitance between the 2. Plus the voltage change that happens in the diagonal neighbors times 2, because there are 2 diagonal neighbors, and the capacitance, coupling capacitance between the diagonal neighbors. Divide by the total capacitance that you have. Now, this turns out that's not a good model. It's not accurate because it's very hard to get it accurate. And it requires knowledge of the coupling capacitance, which is really, really not possible to get from a flash controller perspective. Flash controller knows the delta voltage changes because it is the one that induces these voltage changes, but it doesn't know the coupling capacitances. It requires some sort of measurement that we don't know how to do. So this model is very difficult to implement. So we wanted to actually propose an implementable model. For that, you need to abstract away some things. Essentially, we want a more accurate and easier to implement model. And the idea is to empirically characterize and model the effect of neighbor cell threshold voltage changes on the threshold voltage change of the victim cell. And do this with some distribution fitting. We fit the neighbor threshold voltage change using some sort of model. In this case, it's a linear regression model. And define the coefficients of the model via empirical measurements. So this is our linear regression model. You can see that this is the victim cell's threshold voltage change. It's a sum of neighbor's threshold voltage change with some alpha, which a coefficient essentially we're going to discover, plus the victim's voltage before with some other alpha. So it's really sum. These are the sum effects that change the voltage. And this is the original victim voltage with some coefficient multiplied with it. So you sum up the threshold changes that happen in the neighbors and multiply them with coefficients. So this is a linear model, as you can see, but it turns out it's not a bad fit. So that's the original one. These are the neighboring ones. And these can be measured, basically. So you can measure this, and you just fit the coefficients. You don't need any coupling capacitance information. Okay, so how do you do this? Again, very quickly. It's a lot of distribution fitting, a lot of statistics. You need to extract features based on characterization. Original state of victim cell, threshold voltage change on the aggressor cells. You enhance the linear regression model. And you do some maximum likelihood estimation of the model coefficients. Again, a lot of machine learning techniques can actually do this also. Okay, this is what we found basically. After a lot of characterization, these are the cells that we found that affect the victim cell and by how much. So you can see immediately above cell interference is dominant. If you think about all of the interference that is experienced by the victim cell, 58% comes from this one. And you can see that diagonally immediate cells are almost the same, 11 to 12%. And then the other diagonal, far diagonal, is 1.6%, 1.7%. And then there's also 4% over here. So that's interesting, basically. So far neighbor cell interference also exists, it turns out. This is fascinating, I think. And you can discover these things. Now, basically, it also turns out that victim cells VTH has negative effect on interference. Essentially, if the victim cells VTH is higher, you get more resilience to interference, if you will. That is expected. Okay, so that's our model, basically. Now we have a new model for program interference, which is this. And you can measure a lot of these things. You can ignore some things, of course, based on how important they are. So the most important ones are actually the immediate top neighbor and immediate diagonal neighbors. That's the key. Okay, so we also look at the accuracy of the model. This is on the x-axis threshold voltage before interference. And on the y-axis, this is threshold voltage after interference. This is all measurements. You can see that there is a shift in the threshold voltages. The red ones are measurements. The black line is actually a curve fit. Of course, it's not a nice curve. That's the ideal curve if there is no interference. Ideally, x should be equal to y, right? That's the x equal y curve. Plotted in a weird way, but it's an x equals y curve. So you can see that the after interference voltage shifts. And if you actually correct it based on our predicted threshold voltage, you can actually you actually fit this distribution nicely without actually measuring everything. We basically model it and we predict where the VTH will be before interference, where we know the VTH before interference, and we predict where the VTH will be after interference based on the values around the cell. And this is what we get. So you can actually very accurately predict the VTH shift that will be happening. So this is basically now the curve is the black is not x equal y anymore. It's ideal if the prediction is 100% accurate, and we track that curve really nicely, as you can see. Okay, so basically model corrects for the VTH shift with almost 97% accuracy, which is nice, right? That's what we want to do. We want to predict the shift in VTH before we actually can measure that VTH. Okay, that's this paper basically. The question is, how do you use these things? Essentially, you can use these things to feed a read reference voltage prediction model. So we built models, good ones, bad ones, and over time, better ones. So what do? You can mitigate the effects of the program interference caused voltage shifts. So let's take a look at this picture again. We've seen something similar, right? These are two states, A and B. And read reference voltage affects the row bit error rate. We've also seen that. Here, this is the bit error rate that you get if you use a read reference voltage like this. This is good. And this is the bit error rate you get if you use a read reference voltage like this. And we know that this is bad because the curve is, the area under the curve that's red over here is quite large. You can also calculate it, These are distributions again. So basically, there exists an optimal read reference voltage. That's basically known. Well, you can find the optimal read reference voltage by testing, but you can also predict the read reference voltage if the statistics of the threshold voltage distributions are characterized and modeled, mean and variance, for example. And that's what we're going to do essentially. So that's the idea of optimum read reference voltage prediction. So this is our curves again in MLC. You have 3 read reference voltages. Let's assume you need to do this for every single read reference voltage, no question about that. But this is read reference voltage 3. This is ideal. At some point after program interference, these curves shift, right? And your old read reference voltage is not optimal anymore. You need to predict how much these curves shift, the VTH shift essentially. So what we do is some learning or profiling. And this happens every 1,000 programming erase cycles, because clearly this is also a function of programming erase cycles. We program some sample cells with some known data pattern and test the threshold voltage. And we program aggressor neighbor cells and test the victim threshold voltage after interference. And we basically characterize the mean shift or average shift in the threshold voltage. We call this program interference noise. And now you can actually, based on the modeling that we have done earlier, right? And basically, you can predict the optimum read reference voltage as the default read reference voltage, which was the red one over here, plus a predicted mean shift by the model that's provided by the model. And the model is what we discussed earlier, right? And you do that while the system is running. Every 1,000 cycles, you actually, in the background, you test some cells. The hope is that the cells you test, the threshold voltage shift is applicable to the threshold voltage shift of the other cells, so they're representative enough. You can also collect data over time for every single page, which is also possible. And we have also looked at that, but the area overhead of collecting data per page or threshold voltage shift per page is actually more expensive. You can do it on a per block basis or per drive basis, right? So it's a matter of basically how accurate you want to be versus how much extra cost you want to pay for storing the particular model that's optimized for different levels of granularity. Okay, so this is data in the end. What is the benefit, essentially? On the x-axis, again, we have the number of programming erase cycles. And on the y-axis, we have the raw bit error rate. And the blue curve is, red curve is the raw bit error rate you get if you don't do any read reference voltage prediction. So it's high. If you do read reference voltage prediction and optimize your reading that way, essentially you reduce the raw bit error rate. So this is assuming you implement 32 kbits BCH code. This is your acceptable raw bit error rate. So we get a 30% lifetime improvement at the acceptable raw bit error rate. Essentially, we increase the lifetime significantly without adding more ECC. Or, I mean, you can also do other optimizations, but I'm not going to talk about that right now. So essentially, you reduce the raw bit error rate by about 64%, and you can increase the PE cycle lifetime for a given error correcting code level. So these are the kind of optimizations you can do if you do good prediction. Any questions? Yes. Yeah. Yes, certainly. Yeah, all of those can be done. So all of those can be done. Basically, you can model the threshold voltage shifts after all of these are done, right? Because that's how you will be reading and writing. Certainly, yes. Yeah, you need to take all of those into account, yes. Yes. Yeah, you need to handle the data pattern dependence in some way. It's not perfect. That's why you get less than 100% accuracy. Yeah. Any other questions? It's very good. Okay. So that's the paper that talks about read reference voltage prediction. We've already discussed more accurate and online channel modeling. So you can actually do this read reference prediction more better if you actually model things better. But again, as things scale to smaller node sizes, things become more messy. basically modeling becomes harder and harder as well. So your modeling latency becomes also important. And in this paper, we evaluate different models, for example, for 1x nanometer flash devices. And we see that it's better to use student's T distribution, which has much lower error, but it also has lower characterization latency compared to some other distributions that are actually a little bit better in terms of accuracy. So it's always a matter of accuracy as well as latency, right? Again, I will not go into this, but again, I will mention that this is one of the reasons why flash manufacturers were really forced to develop 3D NAND fabrication methods so that they don't run into distributions like this. This is very hard to, let's say, correct or predict or recover from. Although you can predict, still you need to have a lot more error correction capability, right? If the distributions overlap like this, your error correction capability needs to be huge. Okay, so this is our model, and we basically show that if you do online read reference voltage prediction, you can get based on 3 different types of models: Gaussian, normal Laplace, or student's T. The Gaussian model is not good anymore with scaled node sizes, and these are the actual data points, the stars, I guess. Yeah, they're stars, blue stars. Gaussian and normal Laplace are actually much better. No, sorry, normal Laplace and student T are much better tracking the actual compared to the Gaussian. Although they're also not perfect, as you can see, right? So the actual is over here, and there's some shifts over here. Gaussian is terrible over here, as you can see for VC. VA, VB, VC are essentially VA, VB, VC over here. Okay. So it becomes harder to predict. If the distributions are harder to model and they overlap a lot, it also becomes harder to predict the optimal read reference voltage. Now, if you don't predict the optimal read reference voltage, you can always fall back to what we discussed earlier, right? You retry again. You retry with some other voltage, but now your latency increases. And at some point, you get the optimal. You may not be able to correct the errors again if your error correction capability is not large enough. Okay, this is another data based on what we have measured and what we have modeled. So this is, if you do read reference voltage prediction, we look at the effect on raw bit error rates, and we get better raw bit error rate compared to Gaussian in the end. Okay, there's more basically. There's a lot to read, but this paper is actually a long paper that covers a lot of most recent technology in planar NAND. Any questions? Okay, now let's talk about some more. So basically, the goal is to always develop better models. What is a better error correction mechanism? How can we develop a better model, right? And ideally, for cases where ECC fails to correct a page, we want to have a better error correction mechanism also. So what are our observations so far? We observe that immediate neighbor cell has the most effect on the victim cell that's programmed. A single set of read reference voltages is used to determine the value of the victim cell. We have seen that also. And the set of read reference voltages is determined based on the overall threshold voltage distribution of all cells in flash memory, usually. Now, there's a new observation in this work, which I think is quite creative, and which kind of tackles the data pattern that you kind of mentioned earlier, but in a different way. So it turns out, based on our observations of the threshold voltage distributions, cells with different value, the immediate neighbor cells, are significantly different. The distributions depend on the value of the immediate neighbor cell. Now, how can we use this? Basically, because neighbor value affects the amount of threshold voltage shift that we have seen. A corollary is this, basically. If this is true, which is true, actually, I'm going to show you some results. If we know the value of the immediate neighbor, we can find a more accurate set of read reference voltages based on the conditional threshold voltage distribution, conditional on the value of the neighbor cell. So let's take a look at this. Essentially, you have an aggressor word line and then a victim word line. This is the victim word line before the most significant bit page of aggressor word line is programmed. You have 2 different states over here. And that's aggressor word line now. And this is the victim word line after the most significant page, bits page of the aggressor word line are programmed. These are the values that are programmed. So distributions, overall distribution looks like this. But let's take a look at conditional distributions. Let's take a look at the threshold values, threshold voltage values on the victim word line for those cells who have aggressors that are 1, 1. It turns out their distributions are far away from each other. For those cells who have aggressors programmed to 0, 0, those distributions are also far away from each other. This is, of course, a demonstration. I'm going to show you the real data soon. For those cells whose aggressor immediate neighbors are 1, 0, again, the green ones are also far away from each other, and you get the idea. For 0, 1, purple ones are away from each other. This means that if you know the value in your aggressor word line, you can use a different read reference voltage and different distribution to read the value that you're trying to read. I think that's a very beautiful observation. Let's actually implement it in real flash controllers. We shouldn't have published this paper in Sigmetrics. I should have published in a better conference that appreciates this, because I think this has only 100 references, even though it is actually implemented in all flash controllers. Yeah, of course, we don't do machine learning, right? You don't get 10 million references to a paper. In machine learning, you do something weak and you get 10 million references. Okay, I'm joking. But this is also an example of the fact that citation counts doesn't mean you don't have impact, right? Or low citation counts doesn't mean that you don't have impact. This is actually an idea that I really like. It's very creative. Yes, go. Well, yes, you need to understand all of the temperature effects, but not in this paper. Yeah, temperature is a very different beast. You can control for the temperature. Yes, you can basically control the distributions for temperature levels. Yeah, there is a lot of complexity in these controllers. Yes, you need to take into account data pattern, location, temperature, variations, or there's a lot. But this idea is applicable regardless of temperature in the end. Okay, so the basic idea is use the conditional distributions if you cannot correct the errors with the overall distribution. So you clearly have an overall threshold voltage distribution, and you read using a read reference voltage based on the overall distribution. You don't get the right value. Now go read the aggressor word line, what you have written, and use the conditional distributions to correct things. That's the idea. This is called neighbor-assisted correction, basically. So basically, if we knew the immediate neighbor value, then we could choose a different read reference voltage to more accurately read the victim cell. So overall reading, basically, I already gave you the idea, but this is the overall distribution. You have nothing, you have no knowledge of the values that are written to the immediate neighbor that affected you. You have some distribution, you use some read reference voltage. Assuming you get the correct data, no problem with the error correction code. You don't go to the conditional distribution. The problem happens when you actually have read the incorrect data and you cannot correct it. Now you go and retry. You say, oh, now let me look. Let me try to look at where I got the error and look at the neighbors. And if the neighbors are 1, 1, I'm going to use this other read reference voltage, and I'm going to try to correct those cells. And if I read it correctly, and the ECC can correct it, then I'm done. Right? That's the idea. If I still get errors, then I'm going to try the neighbors with N1, 0, for example, or N0, 0, let's say. If I still cannot correct enough cells, I then go try neighbors 1, 0. If I still cannot correct enough cells, I'm going to try neighbors 0, 1. And then I give up if I still cannot correct enough cells. So you basically do many reads to figure out, of course, you need to read the neighboring word line to know what values are there. And then you do many reads with different read reference voltages based on the immediate neighbors that you have, and you try to correct those cells. That's the idea. Hopefully it makes sense. I think it's a beautiful idea. Essentially, the realization is that you can use conditional probability as opposed to overall probability. So using the optimum read reference voltage based on the overall distribution leads to more errors. I've already said this. So better to use the optimum read reference voltage based on the conditional distribution or value of the neighbor. And the main insight is that conditional distributions of two states are farther apart from each other. If you use the overall distribution, everything gets mixed. Okay, and this is the real measurement from real devices. So this is the overall distribution, pink ones. You can see that there's a lot more overlap over there. And the green ones, the red ones are distribution when direct neighbor is 1, 1. You can see that they're more distant from each other. And the green one is distributions when direct neighbor is 1, 0. And then 0, 1 is the yellow one, 0, 0 is the black one. And I already said what the purple one, pink one is. So there's a small margin between the pink ones, but there's a much larger margin between the conditional distributions. And this is the real data that we measure from real devices. Or if you use the overall distribution, if you the raw bit error rate you get is on the order of 3 times 10 to the minus 4. If you use the conditional distributions, you get much smaller bit error rates, as you can see. Of course, it depends on which one, but they're actually on the same order. Okay, so what is the overall idea? I already given you the idea, basically. You read a page with the read reference voltages based on the overall distribution, because that's easy. Same as today, it's already done, and buffer it. If ECC fails, only if ECC fails, now you try read the immediate neighbor page so that you know the values, and reread the page that you're trying to read using the read reference voltages corresponding to the voltage distribution, assuming a particular immediate neighbor value. You can guide this based on which part you get an error at, potentially, if you have an idea of that, based on the error correction mechanism. Because some error correction mechanisms actually, even if ECC fails, they may give you an idea of which part of the page you have an error at, right? And then you replace the buffered values of the cell with that particular immediate neighbor cell value. And then you apply ECC again. Now, if you read it correctly, no problem. Otherwise, you're going to retry. You reread the page using the read reference voltages corresponding to the voltage distribution, assuming another particular immediate neighbor value. And this is the actually mechanism in the end. At some point, if ECC is correct, you send the data out. But if you cannot correct things, eventually you get an error. Okay, I think I've said everything over here. So the question is, what kind of a prioritized order do you use? This is actually important, and we have some analysis in the paper, but I'm not going to talk about that now. So this is the final result that we have. Basically, if you don't do neighbor-assisted correction, the red is your raw bit error rate for given programming erase cycles that we measured. Now, if you do neighbor-assisted correction fixing based on the distribution, assuming neighbor value is 1, 1, or for those places where the neighbor is 1, 1, clearly you get a reduced raw bit error rate. On top of that, if you use neighbor 0, 1, you get an even lower one. Basically, this is the full NAC, where you actually use all of them. So assuming that you have an ECC capable of correcting 40 bits per 1 kilobyte, you can actually have stages, right? Here is the stage where you cannot continue beyond neighbor-assisted correction. Here is the second stage where you continue with neighbor-assisted correction and you fix the values that have immediate values of 1, 1. Another stage 2, you fix the values not only 1, 1, but also 0, 1. And then the next one, and then the next one, basically. And as you increase the neighbor-assisted correction, let's say strength, you increase the lifetime by about 39% in the end. So 33% comes at no performance loss, according to our analyses. If you want some performance loss, you can actually go higher, 39%. The performance loss clearly comes from reading again and again, right? Yes. And 0, 0 doesn't have any effect. Yeah, I don't know. Maybe they're too close to each other, basically, right? It's a diminishing returns type of effect in the end. I think this may be because of the distribution of the values, etc. Yeah, it needs more analysis, basically. Yeah. Yes. Mm-hmm. Yeah. So that's a great question, basically. So there are multiple effects here, right? Because the value written to an immediate neighbor affects the distribution. So that actually has a big effect on the immediate neighbor, right? That's the major reason, right? Because you actually collect all of the values, right? Because normally, like I go back to this picture that I motivated this with. Where is this? Yeah, this is also a nice picture, but this is the picture basically. So individually, the distributions kind of look like this. But if you collate them, if you aggregate them, you get a huge distribution that doesn't have any distinction between the values. And the reason these individual distributions are like this is because the value, the program interference, the value that you write to the aggressive word line has an effect on the threshold voltage of the victim word line, victim cell. And you can also see this kind of, not as nicely, of course, but kind of, right? And this also, this is measured values. The measured distributions are, the measured overall distributions like this, but individual distributions are far away from each other, right? And the data, the analysis over here actually supports that. It's not as perfect as the original picture, but it's not that bad also. Yeah. Yeah, it's fascinating. Okay, so there's actually performance analysis also. Yeah, you can read the paper for more details over here. This is the paper. Yeah, I still like this idea a lot, as you can see. I think this is a very creative idea, and it is a lot of impact. And never published in Sigmetrics. No, I mean, we had some other Sigmetrics paper that had more impact, but somehow Sigmetrics tends to be not so good these days. Although maybe we should change the publishing model completely, as we have discussed last time. I have another story about that. Now that I visited St. Louis, Missouri in the last week, I have a lot of good stories, but I'll tell that later. Okay, let's talk about read disturbance. Since we talked about RowHammer a lot, what about read disturbance in Flash? And this is another fascinating area. There's another fascinating creative idea at the very end that we will talk about that will try to correct the errors after a flash drive is deemed dead, recover the errors basically. So we already talked about read disturbance. I'm not going to bore you with that. We already talked about NAND flash memory background. And here, read disturbance is very fundamental. Whenever you're trying to read a row or a page, you're applying high pass-through voltage to all of the other pages in the same block. And that's how you induce read disturbance, basically. So we've already seen this, so I'm going to skip these. We've already seen all of these. Let's take a look at this read that we have done. If you want to read one page, you're applying a read reference voltage, potentially multiple times. And while you're doing all of that, you're always applying pass-through voltage to all of the other pages that you're not reading. So that high pass-through voltage actually has a weak programming effect, as we will see. So this is the read that we have done. I've shown you at the beginning of this lecture. You get correct values if there is no read disturbance. Now let's take a look at read disturbance. Let's repeatedly read page 3. Actually, any other page than page 2. But let's pick page 3 for whatever reason. We repeatedly read page 3. You basically induce disturbance errors to all of the other pages, 255 of them, however many you have in a block, because all of them have to be applied the very high pass-through voltage. Now, what does that pass-through voltage has? What kind of effect does it have? It basically has induced a weak programming effect because you're applying that high pass-through voltage. It is really affecting the charge that's inside the floating gates. And it turns out this poor cell over here, which was on the edge 2.4 volts, may go up to 2.6 volts. Now, once it goes to 2.6 volts, it's not going to be read correctly. Right? Now, your error correction mechanism may be able to correct it, but if you get enough of these errors, your error correction mechanism may not be able to correct it either. So that's the idea over here. You get these errors that happen because you apply high pass-through voltage, which causes threshold voltage values of some cells to increase. And if they increase beyond the point where it leads to that cell jumping to some other distribution, or some other voltage range that you deem as another value, then you're actually going to read it wrong, and your ECC may not be able to correct it. Okay, so that's the summary. Read disturb errors actually limit flash memory lifetime, assuming you fix retention errors and program interference errors. Now you deal with read disturbance errors. And it turns out read disturbance errors become worse with technology scaling also in Flash. Okay, we already said all of these. So in this work, we characterize these read disturbance errors. And there we basically have two observations. One is slightly lowering the pass-through voltage greatly reduces the read disturbance errors. So don't use very high pass-through voltages. Of course, if you don't do it in a nice way, then you may actually get errors. Also, read errors now, right? Instead of read disturbance errors, you may get read errors. But there's a lot of actually slack in the pass-through voltage, as we will see. And some flash cells are more prone to read disturb. So we're going to propose two techniques. We're going to mitigate read disturb errors online by dynamically tune the pass-through voltage. Essentially, we're going to find and apply a lowered pass-through voltage value per block, similar to read reference voltage values. You can also do it per block. You can do it per page, etc. Well, in this case, you do it per block because pass-through voltage is actually, well, you could do it per page also, because different pages have different tolerance, right? And we see that you can improve flash memory lifetime by 21% if you do this. And then we have another technique, which is the more, in my opinion, a quite creative one. And we're going to use this for something else also later on. And the idea is to recover after failure to prevent data loss. It turns out some cells are more susceptible to read disturb errors. And if you can figure out which ones are those, you can do some post-failure analyses. You can induce read disturbance post-failure after your device has failed. And you can figure out which ones were susceptible. And you can predict what was the original state of those cells before you induced a lot of read disturb. That's the idea. I think this is quite clever and creative. Essentially, the idea is your drive failed, induce more errors on the drive to figure out what the cells would have been in the first place. It's kind of non-intuitive, but it's actually quite smart. Okay, and this reduces the raw bit error rate by up to 36%. But this is recovery, of course, right? So hopefully you'll be able to recover your data after your drive fails, and maybe you can put it back in operation, actually. Okay, so this is an example where you reduce the pass-through voltage. This is actually real analysis on real devices again. On the x-axis, you have read disturb count, and you can see that the numbers are 10,000, starting from 10,000 to many over here. And you can see that if the pass-through voltage is the maximum you apply, you can tolerate only a small read disturb count. If you reduce the pass-through voltage by 1%, you can tolerate some more read disturbance. If you reduce it by 2%, you can tolerate even more. If you reduce it by 6%, you can tolerate even more, basically. That's the idea, given an ECC capability or raw bit error rate target, of course. So that's the idea, basically. And this is another way of depicting what I depicted over here. This is the percentage of VPass reduction, and this is the normalized tolerable read disturb count. So by 6% reduction in VPass, you can increase the tolerable read disturb count by 1300x. Sounds good. Of course, the hope is that you're not going to induce read errors. Right? If you induce read errors, ECC comes to the rescue. So you can do this smartly when you have ECC tolerance, right? So what does that mean? So let's talk about this tuning. So idea is to dynamically find and apply a lowered pass-through voltage. And the trade-off is if you lower VPass, you can allow more read disturbance, but you induce more read errors, clearly. So read errors, how do they happen? Basically, let's say we reduce things to 4.9 volts. The good news is nothing here is higher than 4.9 volts, so you're going to read everything correctly. So that's good. Now you reduce it to 4.7 volts. Uh-oh, one of them is 4.8 volts, so you read it incorrectly. Right? If your ECC has capability to correct it, great, no problem. So the idea is actually, this is a very general idea. You can utilize the unused ECC capability because ECC is provisioned for some programming erase cycles, right? And you can also apply this to temperature. Again, there are all of these things that you need to think about, not just programming erase cycles, or some retention also, right? In this case, we're going to look at retention. So this is end day retention. And this is the raw bit error rate you get. So ECC correction capability is set for some raw bit error rate, clearly. And if your data is younger, then it has a lot of correction capability, right? That's the idea over here. There's a lot of unused ECC capability for the data that you have just written to the drive. So ECC is really provisioned for high retention age. You can also use this for programming erase cycles, everything. So it's actually a more complicated equation. That's why these SSD drives are actually quite complicated. And you can be very smart about what you do. And there's a lot of room for creativity. So you can use this unused capability to fix read errors, essentially. This is how you trade off between different errors. You have more read errors, and you're reducing the read disturb errors, but you know that you have unused ECC capability. Let's use it for correcting the read errors. Now, unused ECC capability decreases over retention age. So originally, when the data is young in the drive, you can be quite aggressive in your pass-through voltage optimization. When the data is older, you become less and less aggressive. You don't reduce the pass-through voltage as much. And that's the key idea. You dynamically adjust VPass so that readers fully utilize the unused ECC capability. Okay, and the paper has more details on how to actually implement it. But today you conservatively set VPass to the highest possible voltage. It accumulates more read disturbers at the end of each refresh interval, but you get no read errors. Idea is to dynamically adjust VPass to unused ECC capability based on the refresh interval. You just minimize the read disturbers, and you control the read errors to be tolerable by ECC. And if read errors exceed ECC capability, you read again with a higher VPass to correct the read errors. So you have a solution basically when you get errors. You increase the VPass. This increases your latency, of course. Okay, so how do you tune this? Again, this is profiling. I will not go through this in detail, but it's basically what you expect. You estimate unused ECC capability based on when you wrote the data. And again, flash controllers actually have this information. They can keep track of for each block, how old is the data there, or for each page, if you want to spend more, let's say, area. You can aggressively reduce VPass until read errors exceeds the ECC capability. And you gradually increase VPass until read error becomes just less than ECC capability. This is profiling. This way you can figure out what is a VPass that you can use. Okay, so we evaluate this again using real devices, and then we also evaluate it for performance, etc. And we evaluate the overhead, so you can read the paper for more detail. But this is essentially what we get in the end. For different workloads, the average lifetime improvement is 21%. Some of them are actually very much positively affected by tuning because of how often do they retain the data, right? That's why this is a workload dependent thing. Okay, I'll let you read the paper for more detail. But let me talk about this idea that I find also quite creative and fascinating. This could be applied to other type of error mechanisms also. So in the course of this research, we also found out that there is a strong correlation between the effect of read disturbance on some cells, meaning some cells are very resistant to read disturbance. Some cells are actually very prone to read disturbance. And I think this sort of ideas can be applicable to other memory technologies as well. In my opinion, there's more to discover in other technologies too. So let's take a look at what happens. So disturb resistance means when they actually get disturbed, their VTH doesn't increase that much. Disturb prone means their VTH increases significantly. So assuming you apply n read disturbances to a resistant cell versus a prone cell, resistant cells get affected much less. Now, how can you use this? So we have these distribution. Assume that we are looking at only erase state and P1 state. You can apply it to any states, of course. Clearly, before read disturbance happens, there are some read disturb resistant state cells over here, originally in the erase state. These are the circles. R means resistant, P means prone. And some of them are programmed to P1 state. R means resistant, P means prone. Okay, we don't know what these are. At some point, after some number of read disturbs, this is what happens. Resistant cells don't move, prone cells move a lot, and distributions shift as a result. And you get some errors at some point. So basically, the key observation is that disturbed prone cells have higher threshold voltages, right? In each given state. If you apply a lot of read disturbs, the thinking is that disturbed prone cells will accumulate to the right side of the distribution, as you can see over here, and disturbed resistant cells will accumulate on the left side of the distribution. So disturbed prone cells are on the right side of this distribution. They were programmed with ER. Disturbed resistant cells are on the right side of this distribution. And you can say the same thing. Disturbed resistant cells have lower threshold voltages in their particular distributions. And that's also true. Right. Now, how can you use this? Now, the problem is over here. When these distributions overlap too much, at some point you cannot correct things. ECC fails. Now, you have some disturbed prone things over here, and they're actually part of the ER state. And you have some disturb resistant things that are part of the P1 state. But these two are read incorrectly, right? I think. Yeah, I'm pretty sure. This is disturb resistance, which was originally programmed to P1 state. And once you use this threshold voltage, after you determine the optimum, etc., you get the wrong value. And this disturb prone one is actually read also incorrectly. Now, how do you actually use this information? Assuming that you cannot correct any of this, after your drive fails, you back up all the valid data in the faulty block, and you focus yourself on these cells. We're going to look at how you focus on those cells. You disturb the faulty page many, many more times, basically, because you backed up the data. You're trying to, the idea is to identify what is read disturb prone, what is read disturb resistant. You disturb many times, basically cause many more errors. You don't care because you backed up the data. Your goal is to analyze which ones were read disturb prone, which ones were read disturb resistant, and based on that understanding, statistically decide which cells were read incorrectly and which cells were read correctly, and do the correction that way. Okay. And you compare the threshold voltages of each cell before and after read disturb, and you select some cells that are susceptible to flash errors, basically those cells with original threshold voltages that are closer to the reference voltage that you're trying to read from, and you predict among these susceptible cells. And basically, you predict that cells with more VTH shifts after you do the read disturbance 100 times more are more read disturb prone, and they should really be categorized as belonging to the lower distribution, erase distribution in the previous picture. And if you find some cells that have less VTH shifts, they're clearly disturb resistance, and they should have been in the higher distribution in the first place, right? Because they resisted you 100K more times, which means that they probably resisted earlier. So they should be categorized as the higher distribution. That's the idea. And that's the beauty of this idea, right? I like this actually a lot. In the end, it turns out this reduces the total error count by up to 36% after you do 1 million read disturbs. And you have all the time in the world, remember. It's not online, this is offline. You're recovering data from a disk. So an ECC can be used to correct the remaining errors. You can still use ECC after that point, right? Okay, hopefully that makes sense. And this is the evaluation. You can see actually, again, based on real data, if you don't do any recovery, that's your row bit error rate. If you do read disturb recovery, your row bit error rate reduces significantly. Okay. Yes. Mm-hmm. Excellent, yeah. Potentially, we didn't look at that, but I think potentially you could do it, you know. You just need to collect this data online over time, maybe even profiling earlier, right, before the disk comes into, yeah. Yeah, I believe it could potentially have online applications as well. We didn't just do it in this case because it was not easy to do it for us, but it's possible to do it. That's a good idea, I think. Yes. Yeah, I mean, these are good questions. We didn't answer all of these questions. Potentially, my feeling is yes, because this is probably a characteristic of the cell itself. But again, I cannot say that's true all the time. No. No. Probably yes. There's a lot of stuff that you can use for physical unclonable functions, as Ismail can tell you, or random number generation. Yeah. So my guess is yes, potentially. Yeah. People have used retention characteristics for fingerprinting, or yeah, physical unclonable functions in Flash for sure. Read disturbance I haven't seen, but it's potentially possible. They did. Oh yeah, that's right. There's a DRAM work, yeah. But then people attack that also, right? That puff is not very reliable. But I don't know. In Flash, I don't see it. Yeah. See, there are a lot of good ideas. Okay. Okay, maybe I'll cover one more and then we'll be done. Data retention. We're going to apply the same idea for retention also, actually. There are cells that are prone to leakage, and there are cells that are less prone to leakage. And the basic idea that is developed over here for analyzing after, let's say, you get an error, can be applied to retention also. Let the flash drive sit for 100 days after backing up the data, figure out which ones are retention prone, which ones are not retention prone, and then try to probabilistically guess which state each cell is was likely in before the error happened. Okay, so let me go through this quickly. Again, we characterize the retention loss, we optimize read performance for all data, and we recover all data after failure. That's basically what we do in this paper. And again, I will not go into this, but there's a lot of interesting stories like this. People basically write articles saying that, oh, my flash drive slowed down, etc. It happens when your flash drive is older or if it stores old data. So this is a good reason why you should refresh your flash drives also once in a while, because reading from the flash drives that have stored data for many years is not easy, because you may need to do a lot of read retries, for example. Anyway, I'm going to skip these. Why is all data slower? Because retention loss. I experience this all the time. My memory is worse than DRAM these days for some things. Okay, basically, your retention loss, we know what this is, charge leakage over time. And side effect is longer read latency, as we have discussed. And we've also seen these distributions. So this is essentially the characterization of the retention loss. Again, real device data, which is very, very difficult to get, and which was not even present before we published all of this data. I think this paper was the best paper candidate, which doesn't mean much, but I think it deserved it. Or best paper runner-up, I should say. Not all best paper runner-ups are good papers. Sorry. Okay, but basically 0 day means that you don't have any retention loss. Those are the distributions that are the blue ones. 1 day is green. You can see that the distributions are shifting to the left, right? And you can see the 40 day is the black one. And clearly P2 and P3 distributions have shifted a lot. You can also see that the higher voltage distributions have shifted a lot more. So P1 did not get affected that much maybe, but P3 got affected a lot in this particular case, right? Okay, basically cell's threshold voltage decreases over time. And threshold voltage essentially reduces over time, as we have seen. I think we've already said this. First read attempt fails, you may predict the read reference voltage, or you do a read retry. So the reason things get slower is with old data, if you store old data and if you wait for a long time, is flash controller is doing read retry, many read retries, and it increases the read latency. It could also predict, right, based on the distributions, and that's what we're going to do. Okay, I think we've already discussed this. Basically, retention loss require read retry, which leads to the longer read latency. So the ideal read voltage is the optimum read reference voltage. And essentially, you can predict it basically. Opt changes over time due to retention loss. Luckily, it's gradual and unidirectional, meaning it decreases over time. So in this work, we have a mechanism for learning and recording optimal read reference voltage. It's again performed in the background. You could do it daily, you could do it hourly, whatever you can tolerate. Hourly is probably an overkill. And then we have a simpler read retry technique. Here we predict the optimal read reference voltage. If we still cannot get correctable errors, then we do a read retry. If the record opt is out of date, read retry with a lower voltage. That's the idea. Again, I will not go through this in detail, but you periodically trigger an algorithm, and you find and record optimal read reference voltage as per block predicted read reference voltage. And you want to use that next time you read from that particular block. You can do it again across the entire drive, but if you do it per block, it's better. It's all performed in the background. So hopefully it has some more small storage overhead, which is quantified in the paper. And when you actually read the page, you read it using the predicted read reference voltage, which is hopefully close to the actual optimal read reference voltage. But if you don't get, essentially, if ECC fails in the end, you do a read retry. So hopefully you're not using the old, okay, anyway, you're not using the old voltage, you're really using the predicted voltage that's close to optimal. And you may not actually need to use the optimal, assuming ECC corrects the errors because that come up with errors that you experience if you use the predicted read reference voltage. Okay, So that's the idea. Again, in this paper, we do a lot of experiments. We show that you can reduce the read retry count by 30%. You can reduce the decoding latency. No, not by 30%, to 30% of its original value. You can reduce the decoding latency a little bit. And you can reduce the total read latency by doing this prediction significantly. Okay, I think I've already said all of that, so I'm going to not repeat that. But basically, you can use a similar idea to recover all data after failure. We're going to show the same thing, maybe in a better way. So these are the uncorrectable errors that you get even with optimal read reference voltage, right? You have very old data potential. So if you can identify which cells are slow leaking and which cells are fast leaking, you can use a very similar observation that we have used in the previous one, right? So these are two cells. These are the interesting program state, P2 and P3. Both of the states have slow leaking cells and fast leaking cells. And if you read very old data, this is what happens to the fast leaking cells. Slow leaking cells don't leak that much. Fast leaking cells actually go to the left a lot. And you can see that for each distribution, fast leaking cells are to the left of the distribution and slow leaking cells are to the right of the distribution. So it's a very similar observation, basically. Fast leaking cells have lower VTH and slow leaking cells have higher VTH after you actually keep the data in the flash cell without reading for a long time. So the key basically is there's some, we're going to do the same analysis. Assuming that you couldn't actually read from the cell, you look at some risky cells or susceptible cells and analyze whether these are fast leaking or slow leaking. And if you find out some of these cells are slow leaking, you assign them to this state. And if they're fast leaking, you assign them to the state on the right. That's the idea. Very similar idea. We've already discussed this, so I'm not going to go through this again since we're already almost out of time. But the idea is a very probabilistic guess of original state of the cell from its leakage speed property. And how do you do this? You identify risky cells, you identify fast and slow leaking cells, you guess the original states. Risky cell identification is easy because you used an hopefully optimal read reference voltage, and you basically look at the cells with threshold values that are surrounding that voltage. You don't want to do this for every single cell because that's a lot of analysis, right? I mean, you can do it, no question, but you don't have to do it if you want to really focus on the cells that are not read correctly. How do you identify fast low leaking cells? Well, basically, this is what we do. After you get some failure, you back up the data, and you basically leave the data for 12 additional days, or whatever, basically. In this experiment, we did 12. You could do it for 100, whatever you can tolerate, 365. This actually is some folks who find solid-state drives can do, for example. If they want to recover the data in the solid-state drive, they can do a lot of post-analysis of the data. Or if it's your data, you can still do a lot of post-analysis on the data. Basically, leave it and figure out what are the fast leaking and slow leaking cells and attribute them to the original states based on whether they're fast leaking or slow leaking. And again, in the end, we show that if you do this, you can reduce, you can recover 50% of the errors. You can reduce the errors by 50%. Again, there's more in the paper. I'm kind of rushing, but you can read the paper. Again, I think this is a very nice paper, uses another type of insight and has a lot of data on data retention properties. I'm going to skip this, but I'm going to, there's also a lot of work that we did with Facebook on identifying memory errors as well as flash errors. This is the first large-scale study of flash memory errors in the field. I'm going to skip this because we don't have time. In the rest of the time, I'm going to flash a number of papers that you may be interested in. More recently, we've looked at like programming, which I didn't even talk about, but this is actually very interesting, programming interference errors. We've looked at accurate and online channel modeling that I talked a little bit about. 3D is very interesting. So we don't have time to cover this, but this paper, for example, looks at self-recovery effects in 3D NAND and temperature effects. And this paper looks at the early retention loss phenomenon in 3D NAND and some process variation and proposes 4 different techniques to make 3D NAND much more reliable. Some of these techniques are very hard to deploy, but some of these techniques are easy to deploy and they're already deployed. And you can figure out based on the reading of the paper which ones are very hard to deploy. And there's more work on 3D NAND-based SSDs, which we have more recently done, which I'm not going to talk about, but these are all fascinating things, I think. You've seen Flash Cosmos, for example. That is also based on our analysis of 3D NAND devices. Okay, I think I'm going to stop here. Any questions? No? Hopefully you have some creative juices flowing. Yes, there's a question. Yeah. I mean, that doesn't help in the end, right? Because things leak. And if you're not going to read for a long time, in the end, you cannot write beyond some. What you're suggesting is very high voltages, right? Yeah, but then you induce other types of errors, right? If you actually use much higher voltages, then you induce programming errors, etc. Yeah. So there's no silver bullet with simple optimization in the end. Well, you can come up with creative mechanisms that try to identify what happened. Yes. That's a good question. I don't know. I don't know if there's unutilized ECC in DRAM. Or maybe you have something else in mind, yeah. Mm-hmm. Yeah. Yeah. I mean, unfortunately, these findings don't apply to DRAM, right? In DRAM, retention loss is very quick and very fast, and very much it's because DRAM doesn't have this fundamental endurance problem, wear out problem. That I think doesn't apply. Retention is independent of how many times you've written to a DRAM cell, as far as we know, until Ismail discovers otherwise. But I don't think he argues with that part, at least. Basically, you don't have that leverage in DRAM. But if you find some other way, I don't know what that could be. Yeah, maybe you can trade off. Yeah. And also the other issue in DRAM is if you want to, there's some ECC, yes, but the ECC is so small that any let's say, it has very little unused capability, I would say. Whereas if you look at Flash, like some of the ECC mechanisms are huge. Like you have 40 bits for 1000, 80 bits, 100 bits. It's increasing actually. And once you have that, you have a lot of unused capability when everything is going fine, initial times, right? In DRAM, you don't have that basically. You can do 1 bit correction, maybe, if you're lucky. Yeah, but it's good to think about. I think I like the direction you're thinking. Can we apply some of the thinking that we have over here to a much more, let's say, difficult environment like Flash, or like DRAM? And I think that's a very good thing to think about. Okay, I think we're done. I'll see you all tomorrow, hopefully in better weather.